universities are
This
not,
meeting is being recorded.
the universities are not yet developing much curriculum in this particular area. There's a couple that actually have started, and I'm trying to do something at USC. And I heard they probably have this class at UC Irvine, possibly in sustainable aviation, but most of the universities don't have it yet as an elective or an option. I've added it to my class, which I'll talk a little bit about in aircraft design, as a single lecture, similar to what you're going to see here. Also, there's interest in giving this as a short course, and I'll show you there's short and long short courses with this material that I will mention as we go here. So that's interesting. What I'm going to be showing today, both this first session on sustainable aviation and the second session after lunch on electrified aircraft, is material that I presented at this ITEC conference this year in Anaheim. That's sponsored by the IAAA, so the electrical engineering people. It's focused on ground and air transportation, but most of it was ground transportation. They did some air, and they teamed up with the AIAA. I'll show you a little bit more about that. And so I gave essentially these two different, they called them tutorials. They were about 90 minutes each in Anaheim this summer. That's why you see actually reference to June of 2022. And I'm essentially doing similar material, maybe a couple slides changed and shifted, but using that for this activity. Okay. So the first tutorial, we're going to talk about history and current developments in sustainable aviation. We'll learn about various topics. We'll cover very briefly some of these, some in a little bit more detail: noise, alternative fuels, a little life cycle, environmental impact, results, things like that. We'll talk about advantages and challenges of each of the alternative fuel and energy types, and then electric aircraft, as I mentioned, will be discussed after lunch today. So I'm going to welcome you to the sustainable aviation community. It's kind of a growing area within aviation. And I want to do some promotion of the AIAA activities related to this. We had the conference in June, co-sponsored by the IAAA, this ITEC plus Electric Aircraft Technology Symposium. Coming up in January, there's this regular SciTech conference where there will be material related to sustainable aviation, but not specific focus. And then there's the Aviation 2023 conference in San Diego coming up in June of 2023. And the Electric Aircraft Technology Symposium will be part of that. So I'll be down in San Diego all week working on doing those kinds of things. So that'll be really a really good place if you're interested in this area. Some of the things that have happened: short courses. We finished up a short course on design of electrified propulsion aircraft. Most of the AIAA short courses now are being offered online, live online, and then they're recorded. See, we did that in July of 2022. You can probably get recordings of that if you want to dig into that. About 2 years ago, I did a 4-hour short course on sustainable aviation, and you can go to the AIAA site and get that on demand for the prices you see here. Okay, what else? There's a neat course coming up relating to batteries and fuel cells for aircraft type systems. That's kind of starting in April of 2023. And that's, these are the usual kinds of expensive prices, right, that you see for full short courses. I'm giving the 10-hour version of this course. God help you if you want to go see 10 hours on this, as opposed to 90 minutes. But I'll be doing that in May of 2023, so that'll be coming up. That will go right in much more detail in all the areas. And then there are committees, right, in the AIAA. There's no single committee that covers this because it crosses different areas. There's an electric aircraft technology technical committee. There's a green engineering committee. There's a transformational flight committee. There's an aircraft design committee. The gas turbine committee is interested in this area as it relates to turbine engines, things. So if you want to get involved in a technical committee, these are the committees that are doing something in the area of sustainable aviation. My information, I'm a fellow of the AIAA. I retired from Boeing 2 years ago as a technical fellow at Boeing, working in this area. You'll see sustainable aviation kinds of things. I'm not speaking for Boeing today. I'm completely speaking as an independent consultant. It's amazing, but I've actually been working 38 years in aerospace. Seemed like only yesterday, right? I was just starting out. I do work for several different companies, but I've done a fair amount of work for Electrified, which is doing an electric distributed propulsion short takeoff and landing aircraft concept. And so they're working on that. I did a lot of work at Boeing. You'll see some of it here. Really started getting sustainable aviation thinking at Boeing going, and we looked at all kinds of different things. But over my entire career, I've looked at many things, including all the way from space launch vehicles all the way to hypersonic vehicles, things like that. I worked on a lot of NASA studies related to the sustainable aviation area. I've gotten all of my degrees from USC, see here. I made sure to schedule around any USC football games. They played last night. They won. That's great. So there's no conflict today with any football games, so that was good. I teach aircraft design for seniors at USC. Okay. A little bit of, why do we want to fly? What's the motivation for that? And this is from the Air Transport Action Group, which is an industry organization of airlines and aerospace companies. Aviation spurs a lot of economic growth. There's every day 120,000 flights carrying 12 million passengers, and they carry $18.8 billion of world trade. There's also a social aspect to aviation in that we're connecting people around the world, right? So we feel there's a real benefit to being able to visit other cultures. There's, it goes far beyond money. It involves connecting people, and it involves also seeing other cultures and hopefully getting along with them better because you're able to interact with them directly. So, there are real benefits to flying. The answer to reducing the environmental impact of aviation, we don't feel is to stop flying. I think that's not the answer. So we want to make it as environmentally friendly as possible to minimize the environmental impact of aviation. So what is the definition of sustainable aviation? I have a definition of sustainable: produced or sustained for an indefinite period without damaging the environment or without depleting a resource, renewable. And then specifically, the way I see it for aviation, I see it as a cleaner and quieter future for aviation. Reducing the environmental impact to the point where there's a general consensus that the benefits of travel by aviation balance its environmental impact. Right? A lot of people are trying to say, let's make it zero environmental impact. And I think zero environmental impact would be if you stayed home in the dark, that would be zero environmental impact. I don't think we're going to get there. So let's minimize it. And so it's good, a good balanced part. We're doing our part to minimize the impact on the environment. And then from a business standpoint, we need to take action so that we can continue to do business as the aviation sector into the second half of the century. There's certainly a lot of pressure, right, to reduce the impact, and you'll see some of the goals that have been set for 2050, right halfway through the century. So, there may even be a few people that think climate change is ridiculous and stupid, but if your company and your customers think it's a big deal, then you have to think it's a big deal as well. So I'm not going to try to argue any of that kind of stuff. But you could take the position that I think climate change is exaggerated, but I still need to address it because I'm in a world where the majority of the world thinks it's very important. That's fine. We don't have to have that discussion. Okay. And things like flight shaming are real, right? People are out there saying you should not be flying, it's bad for the environment. There's a lot of truth to that, and we'll get into some of that. The pressure's there. You see it in the news every day. Having a worldwide climate summit as we speak. They're setting goals. They're trying to figure out ways to reduce the environmental impact of everything, reduce CO2 and other greenhouse gases. So a lot going on. Certainly plenty of pressure to say clean up our act. Like I said, if you're trying to sell airplanes to people, here's what people buying airplanes are saying. How important is environmental sustainability? 41% of the customers said it's very important, 30% extremely important. Not very many down here on the tail here are not very important at all. So the customers want it, the passengers want it, the airlines, people that would buy your products are also very, very interested. And then there are policy things that are happening all the time. This was a big news item when in France they started to bail out their airlines in response to the problems with COVID, right? So one of the things they basically were saying is, we will go ahead and, Air France, we will give you money to help keep you alive and to do these things, but we don't want you flying some of the routes that can be done with trains, which they felt were lower environmental impact. And so that's why it says with strings attached, right? They help bail out airlines, but they're putting strings on. Not necessarily in the US have they done that, but certainly in other places, right? They want aviation to inherently become more sustainable. This actually, it's not like it just started. Here's a cover of Aviation Week from September of 2010, talking about biofuels and advanced fuels of different kinds. As I went back, I started thinking about this about in the year 2000. Honestly, the reason I did it is because I was working in hypersonics, and the funding for hypersonics was at that time collapsing. So there was very little work to do. So I got enough flexibility from my boss to study a few different things. I looked at a little bit on homeland security technologies, but then I said, let's look at this environmental impact of aviation. So that's when I started looking at it. It had actually been worked on before that in the mid-60s and early 70s on something called the Supersonic Transport Program, which some of you might remember. Then there was a high-speed silt transport program. So Supersonics was looking at what their environmental impact was, and then the Supersonics kind of collapsed. All we had left basically was the Concorde flying a little bit. Everything else kind of collapsed. And so the work on the environmental side kind of collapsed with it. The terminology shifted over time. We used to call everything green, now we call it sustainable. We used to talk about biofuels all the time, now we say SAF, which is sustainable aviation fuel. So the terminology has changed some over time. So today I'm going to talk a little bit about noise, emissions, fuels, and then do some wrap-up comparisons. And we'll talk a little bit about environmental life cycle assessment, kind of at different times as we go through here. I'm going to talk about noise because it doesn't exactly fit into some of the other sustainable things, but one of the biggest drivers on aviation's growth is whether you're adding airplanes that create more and more noise, right, that are bothering the local residents and things like that. The FAA gets way more complaints about noise than they get about emissions or anything else. And so it's a big deal. It's something you want to consider just as important as the emissions when you're looking at the design of aircraft. So there are some fairly good discussions of noise in some of the typical aircraft design textbooks, like Nikolai and Lamer have some sections on that. I pulled a few things from there. Basically, the noise comes down to they measure the noise, or they estimate the noise at 3 different points during approach, and then at takeoff, downrange, and then to the side. Basically put microphones, right, and they measure how noisy your airplane is as it's taking off and landing. They don't pay much attention at other flight conditions. And so you see the terminology they use has to do with these noise values, either separately or total together, and they use decibels, dB, you'll see. And I'm not going to go into an explanation of the mathematics of decibels versus pressure disturbance, pressure delta, but that's the terminology that you'll hear, right? Lower is better, it's pretty clear. And so they established limits, and this international organizations get together and they assign these different levels of noise. And here you see a noise in this is stage 3, one of the levels, EPNL, dB, so this is the noise, pressure, disturbance in decibels from the noise. And you can see what they allow. The x-axis is the weight of the airplane, right? So they allow larger airplanes to be noisier than smaller airplanes. And the reason they do this is because these kinds of internationally agreed regulations, they try to do something that will push the state of the art. They do recognize the laws of physics and the basics of aircraft design. And inherently, the larger engines creating more thrust are going to be noisier on a proportional basis, and so the larger airplanes are allowed to be noisier. What you see though, here's for similar kind of thing versus time. These are the different levels they allow. And you can see the clear trend is to lower the noise levels that are allowed by airplanes. The other thing you see is there are very few airplanes on this chart that don't meet that, at least the ones that are current, developed during, in 2010, here's an outlier airplane of some kind here. But most of the airplanes, the newer airplanes are all meeting that. Even most of the previous generation airplanes are going to meet the new rule, which they call Chapter 4. Now we're talking about Chapter 14. So again, what they're doing is they're trying to essentially decrease the noise of the fleet. And they usually do that by only identifying a few noisy outliers, and they kind of put those above the line. So they're not trying to force the entire industry to swap out their entire fleet, but they're trying to get rid of the noisiest airplanes over time. And that's what happens when you have an industry group setting the standards and kind of work into that. There are some individual airports can set more stringent standards and require some other things, like Orange County Airport has additional restrictions. Some airports restrict the time of day that airplanes are allowed to fly. So there are more things that some of the airports can do, but generally these are the rules. So new airplane design now is going to have to meet this. Going into service would have to meet this Chapter 14. And there'll be another one, right? They'll get quieter as they die out in the future, so there'll be a noise. A lot of different noise sources on an airplane. This is a chart out of Nikolai's book. But you can see, here's our airplane. There's aft fan noise, forward fan noise, combustor noise, turbine noise, mixing of the jet with the free stream, airframe noise of different kinds. So different sources, and we'll talk. This figure, right, is very fighter airplane focused. For commercial airplanes, during approach, it's mainly the airframe, and the fan is the biggest contributor to the other noise directions. So in a commercial airliner, the combustor, the turbine, the compressor, there are no shock waves in the exhaust. Those are not usually significant. The most modern airplanes, during approach, for example, the airframe may be the noisiest source. It may be quieter than the fan. The fan is at a reduced power condition. And then there's a lot of discussion. We won't get into too much on frequency. So these all have different frequency responses, and they're loud at different frequencies. And so when they're combined, you need to look at the frequency as well as the amplitude. Other implications of that are different frequencies of noise transmit through the atmosphere with different losses, right? So high frequency noise will fade faster than low frequency noise as it propagates through the atmosphere. So if you're doing noise analysis, those are all the kinds of things that you would apply. Some of the noise sources on an airplane, like I said, the engine fan, both in the inlet and the nozzle, those are important. The engine exhaust, the landing gear creates turbulence and noise. High lift systems create vortices and noise, especially at the boundaries between flaps and things like that. Interior noise is also important. We'll talk about that a little bit. They're able to image noise using an array of microphones. So you fly your airplane over a microphone array and get this kind of data. Here's an airplane. It happens to be a fuselage-mounted rear-engine airplane, so you can see the jet noise coming off of that. You can see these two blobs here. Anybody have any idea what those are?
Landing gear.
Landing gear, that's the main gear. This is the nose gear up here. And over here, this is the flap interaction, the edge of the flap and the wing creating a vortex and some turbulent flow around that area that's also noisy. And so those are the kinds of things, right, that are creating noise on an airplane. There are things that are done, they try to mix out faster to reduce some of the noise. So you see these lobes. Here's a trailing edge of a nozzle. Here's a mixer inside the engine. Those are all geared for trying to mix it out. There's a lot of noise is the difference in two velocity streams against each other. So if you can mix it out, then it won't be making noise anymore. So you see these kinds of features on jet engine. Interior noise is important. There are communications that have to go on in the cockpit. The pilots have to be able to talk to each other. In the cabin, passengers want to be able to have maybe not a completely normal conversation, but some kind of conversation that goes on. You need to make public address announcements. Even though flight attendants are great at reading lips and things, it helps so that they can actually hear you, as well as it's just more comfortable to not have a lot of noise. Some of the sources of noise inside the airplane come from the outside, the flow around the outside of the airplane. The engines, right, obviously are a source of noise. The air conditioning system inside an airplane, the flow of the air around circulating in the cabin can also be quite noisy. Those kinds of things. Okay, so just a little bit on how the noises vary. We'll see if this works. We've tried some of the audio-visual things, and we tested this out and looked a little bit earlier. We'll see. But this is the difference between fan and a propeller in terms of the kinds of noise that it makes. If you're a noise expert, you get very good at hearing the different frequencies and understanding what they are. But for the rest of us, it's kind of a black art a little bit. But let's show you a couple of examples. So a fan tends to have a higher frequency noise, and it also sounds different. I'll see if I can play you a clip of it. Also, the directivity is different. In a fan, in a duct, most of the noise goes forward and backward directly. In a propeller, it's open, and most of the noise goes out radially. Right, so we have a different directivity of the noise, but you should be able to hear the noise here pretty clearly. All right, so that's a relatively high frequency fan noise. Similar kind of device producing a similar amount of thrust might sound like this for a propeller. Right, these are kind of almost cartoon-like noises that you're used to hearing, right? You could probably tell that one is a propeller and one is not. But that's just the beginning, right, of a lot of kind of detailed analysis that can be done to figure out the noise of airplanes. But just a little sample of some of that. Okay, I'm going to move on to emissions. We'll come back at the end and go with questions. If you have a specific question related to the content, go ahead. It's relatively short. I encourage you to bring it up. So any questions on noise before I move on? We can come back to it if you have a question. Ken, how are we doing?
Very good.
Online audience is doing okay?
Yes.
Okay. All right, so let's talk about emissions, right? CO2, carbon dioxide emissions, that's what most people talk about, so let's talk about that. This is a chart out of The Economist magazine, which I pull a lot of things out of there. In the US, greenhouse gas emissions by sector as a percent of the total, and all these bars together add up to 100%, so you can read them this way. So agriculture, 10%, commercial and residential, a little more than 10%, industry, a little more than 20%, the electrical grid, electricity generation, more than 25%, and then transportation, right, totaling a little less than 30%. Light vehicles, right, that's cars. Heavy vehicles, those are trucks. Here's our aircraft, and then others, including trains and boats and ships and all those kinds of things. But you see, aircraft is we're not even close to being the biggest source, but everything counts, right? So we don't get out of trouble by just saying we're not, the trucks pollute more than we do. We don't get out of it just by saying that. And you'll see there's some other features that we have to worry about. This is one of many, we call these the wedge chart. It's what the industry did to propose a roadmap of how they can reduce the emissions of aviation. And they started back in time laying this out. This has been adjusted for the COVID decline in flights and all those kinds of things, now that and the growth back up again. But what they do is they have projections for what the market and commercial aircraft is going to do, and the number of airplane flights, and the number of people that are going to travel. And so that's kind of what the top line is if you just took today's airplanes and kept flying them. And of course, it's going to go up a lot. It may even double or even triple depending on the model that you do. And that doesn't seem like a very good idea from an environmental standpoint. These other bars are doing things like, as you replace older aircraft with newer, more efficient aircraft, you come down. As you operate more efficiently by flying the aircraft within the air traffic management system, that you can reduce the CO2 emissions and CO2 emissions on the y-axis. The big green zone is what you're talking about, sustainable aviation fuel. What can that do for you? So that they're trying to do that, use sustainable aviation fuel for this, and then they rely on, if they can't make that happen, they've got in their notional look here a relatively small, this gray area called offsetting. So that's policy measures where you're buying an offset from a more polluting industry that's cleaning themselves up more cheaply than you can, and you buy those credits and you use those. So that's shown as a small part. If the technology and sustainable fuels and all that stuff don't work out, a bunch of this big green bar over this green section over here is going to turn gray, and they'll be buying offsets instead of reducing emissions directly, so we'll be reducing indirectly. So that's kind of the plan. And what the whole industry has been wanting to do is to get out in front of worldwide regulation. They don't want to be banned from flying or told to reduce their flights by 50%. They want to be able to show they have a coherent plan to make aviation sustainable, so that the governments will essentially endorse that rather than, what would you call it? Rather draconian measures to stop flying. They don't want that to happen. So they've been working on it very hard for quite a while. And you'll actually see the history of the wedge charts is interesting. In the longer class, I'll go into it in more detail. But I'll show you another version of this chart that's more current. This one's only a couple years old, but the target has moved between 2 years ago and today as to where the industry wants to go. Another reason for concern that aviation has, is it looks like, the prediction is it'll be easier for other sectors that are producing greenhouse gas emissions to reduce their emissions than aviation will. So here's a chart. It's got everything from, it's got passenger cars and trains and trucks and buses and all these things in here. And these are emissions versus time. Where are we today? We're over here, 2020. Right, so aviation is this part of transportation. We saw that in another chart. But it's much easier, it looks like, to electrify ground transportation, and relatively easy to electrify rail, for example. So as those things occur, this shows aviation making some reductions, but out here in 2070, aviation could be 40% or more of the transportation emissions. And they want to short circuit that. They want to reduce that. So they're not considered the single worst contributor to climate change in the transportation sector. So they'd love to avoid doing it. And here's the latest version of the wedge chart, right? A little more colorful than the other one. Essentially, it has the same features, but the goal is shifted to zero net emissions in 2050. That's the worldwide goal that's been set, and they're trying to get to that. And they still have a lot of work to do. We'll talk about how attainable that might be. But this line assumes 50% emission reduction for sustainable aviation fuels, and then this one shows 100%. And that's basically what they need to get to. They need to get away from burning fossil fuel derived jet fuel and use extremely clean, virtually zero net CO2 emission fuels. And then we'll talk about what might be possible there. It's a very difficult goal. You might argue that it's an impossible goal. We'll have to see how that comes out. How close can we get to zero? And what we don't make, we have to buy from other industries. That would be what would happen. Okay. So let's look at the emissions a little bit, kind of one at a time. We'll do some background on climate energy first. So some more charts kind of on contributions to greenhouse gas emissions. You can see electricity production, similar to what I showed before, 25%. Transportation, 14%. You can see some of the other greenhouse gas emissions. In terms of by country, you can look at that too. The United States is kind of second behind China. China passed us up some time ago in total CO2 emissions. Other developing countries are a big deal as well. So it's like everyone's got a part to play. I think that's kind of the theme that that they're trying to talk about at the climate summit that they're having currently. Right, lots of things going on, including the poor developing countries want the rich developed countries to help them pay for becoming more environmentally friendly and fuel efficient, all those kinds of things. So a lot of things going on, but you certainly need China and the U.S. and everyone to do something. Right? Everyone's got a role to play in this. It won't be successful if any of the big players are not fully engaged. Okay, electricity generation in the United States versus time. You see just, what do we have here? Coal peaked before 2010 and has been falling off to a lower level. Renewables have been picking up. Here's the green line, and they're projected to continue. Natural gas essentially has taken over for coal, so it's been growing and expected to grow in the future. Nuclear is kind of stuck. There's not enough public support and government support to really do a lot of nuclear expansion. And talk a little bit more about that, but that's a big deal. If nuclear could ramp up, that would help some of these other things. But that's kind of the way renewables look. I think the next slide zooms in on renewables in the U.S. Hydroelectric power, right? Here, there's just a limited number of places we can add dams and turbines in order to create hydroelectric power. So the projection is that's basically stuck at that level. There's some geothermal things that can be done with that. There's only certain sites for that. So it's wind and solar that are going to do most of the work. They're both expanding pretty rapidly. The projection is that there'll be diminishing returns on where they put great big windmills. Offshore wind may extend this a little bit more, but it's going to be eventually solar that is what takes over a lot of the environment, a lot of the clean renewable energy in the United States and around the world. One of the important implications has been over time is the cost of all of these renewable energy methods of generating power have come way down, and so the renewable methods are now cheaper than the conventional methods. So that is a really good thing to have happen. And you can argue that developing countries, it makes more sense for them to skip over coal and other highly polluting things and go directly to solar and wind. The issues being, how do you make a stable electrical grid when the sun doesn't shine? And there's a lot of issues involved in that. So that's it. Battery storage is shown on here. That basically is what you need to make your grid stable 24 hours day, and that's still pretty expensive, so that's something that's being worked pretty hard. So adding some energy storage into your electrical grid makes it more stable and enables you to add more and more renewables that might be transient, like solar and wind. So you can kind of see that. But the important thing is that the renewables are actually now cheaper than doing coal. They're even cheaper than doing natural gas most of the time. So that's a development, right? It wasn't true in 2010, but it's true now. Lots of charts. The global temperature is on average going up. Um, it seems clear, to me it seems to the point where you can actually notice it on a year-to-year basis. As a human, having lived on the Earth for 60 years, you can actually notice that the change has been happening. There can be arguments about how much of it is due to what causes. We'll skip all those, but definitely, it's happening. Temperature's going up. What can we do about it? We all talk about CO2 all the time. It's not only CO2. CH4 is methane. That's also a contributor to greenhouse effects, to the rising temperature. We have. So if we look at the power per square meter change in forcing, which is the temperature going up and down from this power hitting a square meter on the Earth, 1.46 watts per meter squared are from CO2, but 0.5 watts per meter squared are from methane, CH4. And then other things, various combinations of nitrogen, oxygen, different molecules, those are like 0.15 watts per meter squared. So those are smaller, but they all happen. So one of the things they mentioned at the climate summit, I think yesterday or the day before, is the US is using their NASA satellites to identify methane leaks and emissions, which they will then try to stick somebody on to try to reduce the leaks, improve efficiency, those kinds of things. So, so it's mostly CO2, but the other ones can be important as well. And there's different time frames, which we won't get too much into, but methane does not stay in the atmosphere as long. Carbon dioxide stays 100 years or more. So it's the hardest to deal with. Okay. All right, so a little bit of what comes out of an aircraft engine when you burn fuel. What mostly comes with the chemical reactions that give you the heat, that give you the acceleration, the velocity that gives you the thrust, produce, right? You have carbon-based fuels combining with oxygen, carbon and hydrogen-based fuels combining with oxygen, so you get carbon dioxide, CO2. And you get water vapor, H2O, and those emit, when you do those reactions, heat is released. That's what gives you the thrust, makes the airplane go. A lot of the emissions, though, are based on just kind of small things that come out, not those two major molecules, but things like carbon soot, carbon monoxide, different kinds of NO molecules. If there's any sulfur in your fuel, it comes out as a sulfuric SO something, sulfuric acid, things like that. If you don't burn all the fuel, you get unburned hydrocarbons that come out. And a lot of the health problems that we have to do with these the small amount, the sliver of really polluted, pollution that comes out. And then the environmental impacts relating to climate are mostly from the water and the carbon dioxide. And so let's talk a little bit about contrails. So this picture again, but these big trails, right, that come from behind the airplane. This was over my house, right? This is the kind of thing that you just see looking up in the sky, and not every day, right? Some days, depends on, we'll show what it depends on, but sometimes you see these trails everywhere, sometimes you don't see any. And then sometimes they hang around, and a lot of them end up turning into what you would think is clouds, but they are clouds, but they actually were induced and started as a contrail that some airplane left. And these have an effect on the temperature. So a little bit on contrail formation. We talked about the main products of a hydrocarbon fuel, which is most of the fuels that we burn, carbon dioxide and water vapor. The water vapor exhausts into a cold environment up at high altitude. The exhaust is hot because we've gone through this chemical reaction. It cools down, and it can bring the humidity to the point where it'll form water vapor, or it's cold enough, ice crystals. And those are what form the contrail. It's a complex chemical process. It depends on many different kinds of things. But sometimes the contrails will just appear for a short distance and then disappear completely as they reach a point where they get warm enough where the water vapor goes back to being just normal water molecules, and you won't be able to see them, or they turn into ice and they persist in long contrails, and we'll see a little bit more about that. But why do we care about that? Well, it has to do with energy balance. So here we have a picture. The sun is coming down. If there's a cloud, either the cloud, a natural cloud, or one formed by contrails, the effect is kind of the same. It does reflect some of the sun's energy back into space, but a lot of it goes through. And the stuff that goes through then warms up the Earth, and it re-emits at a different frequency that is mostly trapped by the clouds, and so it gets radiated back. And so during the day, it's kind of a mixture of which effect is larger. Are you reflecting more away, or are you holding more energy in when you go through a cloud? At night, though, right, there's no sun coming in. All you're doing is keeping the planet, the surface warmer by having a cloud. And so the more clouds you make, the warmer you're going to be at night, for example. Also says things like contrail formed by an airplane at night is definitely going to have a warming effect. The contrail formed during the day may or may not have a warming effect. So those are the kinds of considerations.
Okay.
Okay. Do we have a question? Maybe just an open mic. Okay, so here's a chart called the Appleman chart, which people use to understand contrails. Let me take you through it a little bit. On this axis is the temperature in degrees Celsius, and we start at this flight level. These are like referred to by pilots in aviation and things, but this is 20,000 feet already, 30,000 feet, 40,000 feet, for example. So this doesn't go, if we extended this all the way to sea level, these curves would look, the temperature would look like something we are more used to seeing. But as you go up in altitude, it gets cooler. And then the pressure, this is the pressure of the atmosphere, and it's dropping off as you go up in altitude as well. And if you follow what the standard atmosphere that we use for modeling is, that's what this dark black line is. So at 20,000 feet, you can see that here's the temperature and here's the pressure. And then drawn on this are lines based on the chemistry, the properties of the water, the pressure, temperature, the water, all that stuff, whether you can form a contrail or not. So this first line is the boundary where to the right of this line, no contrails are going to form. And then in this zone, between these lines, contrails are possible, and then to the left of this line, very likely a contrail is going to form based on the pressure and temperature conditions. So if an airplane is, say, climbing along this normal line from 20,000, 25, as soon as they get to about a little below 30,000 feet, they're in a zone where a contrail might form. And they continue to climb toward a cruise altitude for a commercial airliner, 35 to 40,000 feet. Oops, it's pretty typical. So at some point between point A and B, it's likely the airplane is going to start forming a contrail. And then it goes out to this point where it's modeled in the atmosphere, the constant temperature zone goes up this way. The interesting part is, if you optimize an airplane to fly for minimum fuel burn, maximum efficiency, one of the spots they like to fly is right over here, which happens to be the zone most likely to produce contrail as well. So you can see that we've put ourselves in a position where we're flying most efficiently in a zone that it's very likely to produce a contrail. Got a question in the back?
Yeah, quick question. What is the difference, like business aviation? I mean, those airplanes that they fly higher altitudes, right, like 50,000 foot level. Is there like any discernible difference in terms of contrail formation between them and regular commercial aircraft?
This model shows that at some point they're going to have a reduced chance of making a contrail at a high altitude, but they probably can't go high enough to get away from it completely. Yeah. So business jets often can fly above 40 or even 45,000 feet, maybe. So there are other issues related with flying even higher that will come into play for supersonic airplanes that also fly at higher altitude. So the solution isn't, I don't think, to go higher. Most people that look at this say the solution is probably to be able to predict when you're going to form a contrail and then fly lower.
I have kind of a general question on water. I think it's a more potent greenhouse gas than some of the carbon based gases, and I don't ever see much of an analysis of trying to turn water into something other than water.
Well, water, if water doesn't form a contrail at the altitudes we're talking about here, it usually falls out of the atmosphere within a relatively short period of time. And so even though it's a more potent greenhouse gas, it doesn't last as long, so it doesn't have nearly as big an influence as CO2 does. Unless it forms a contrail, then it has a much bigger effect. So most of the discussion that I've seen has to do with trying to do something to capture the water to keep from forming a contrail. There's an issue at higher altitudes on supersonic airplanes in the water. If you put it up high enough in the atmosphere, it stays a lot longer. It takes a lot longer for it to come down as rain, essentially. And so it can be a bigger deal for supersonic airplanes flying at 60 or 70,000 feet.
Mr. Professor, what do you think about third generation microalgae in the oceans? We can think 3D, right? Excuse me for my English.
Yeah, can you repeat the question, please?
Yes. What do you think about the third generation of microalgae? Microalgae, you know?
Sequestration of carbon in the ocean?
Yeah, yes, in the ocean. We can think 3D, no?
Yeah. Microalgae. Yeah. I think we'll talk about that a little bit more later. But yeah, that's one of, it's kind of a non-aviation, there are non-aviation ways of reducing CO2 in the atmosphere. If you use algae to capture, when algae grows, it's gonna suck in CO2, and then you can use that as a feedstock for sustainable aviation fuel. Right, so that's a possibility too. We'll talk about that. Okay, let's see if this plays. We're not quite sure. This doesn't work. These are some videos of contrails and contrail activity.
Thanks, sir.
Yeah. Two of them, no? It's a 747. See how the guy is, yeah. Amazing.
Okay, what we have here is we have someone that's in a 777 airplane taking a video up above him, and there's a 747 and a 737 above, and they're making contrails. And here's an example, right, of contrail formation. And the conditions are such that they're forming these contrails. One of the interesting things is how excited the pilot is. I mean, he's probably a 20-year experienced pilot, and he's seeing this, and he's pretty excited because it's very rare that you're going to see multiple airplanes all kind of stacked up on top of each other. That's kind of fun.
That was one of the rarest.
Yeah, okay, so. All right, and then here's another video. This one, if it works, we'll see how this works. Okay, so I'll stop it. What you see here is you see two airplanes again. It's being viewed from another airplane, but this airplane is coming at us. The contrail does not persist. if it flies by, you can see the contrail doesn't die. So it's an example, right, that some of the contrails do not persist. It depends on the conditions, and these are all the things that you need to calculate to figure out if you're forming a persistent contrail. Okay. So a little more discussion. How do contrails compare to say just CO2 produced from aviation and other mechanisms? And here's a chart where this is the forcing terms, and we won't go into the details of this, but it's watts per megawatt or milliwatts per meter squared are the units down here. But so the bigger the number, the worse it is. Some of the numbers may be negative, and they're shown here too. And also shown are the uncertainty bars, right, on how much error there could be and what the value is based on the data and methods that people have. And so CO2 is this value, and the modeling shows the CO2 effect is within relatively short error bars. Contrails, though, the effect potential is very large, maybe double the CO2 itself, but with large uncertainty bars around it, depending on conditions and the flights and errors in the modeling involved. So that's why people are concerned about contrails. They have a big effect. Other mechanisms are also kind of for these ones related to NO and X is like, that means NO, NO2, NO3, those kinds of molecules. They have both positive and negative effects depending on the way the chemistry works. Generally, those kind of cancel out. Water at the altitudes flown by commercial aircraft doesn't have much of a greenhouse effect. Pollution from particles, aerosol radiation actually has a little bit of a cooling effect. And so these are some of the total effects here, but contrails are a big part of that, and that's why we are working on that. All right, here's another picture showing they over time a lot of times the contrails become these cirrus clouds. People are working hard. They figured this out. If there's things they need to do, they're conducting trials of rerouting airplanes, changing altitudes, things like that. And so there's activity going on in Europe and the Middle East, and the NASA's gathering some data in different ways. So they're working to see how they can fly the airplanes and avoid forming the contrails. And if they do, right, they can significantly reduce the impact, some of the impacts that we've shown. The other thing that comes into play is a lot of short-range flights. If you're flying a few hundred miles, they may not ever get to the altitude where a contrail is going to be formed. So that would say some of the shorter-range flights, LA to San Francisco, maybe is not going to form as many contrails as a flight that goes across the Pacific, for example, which will fly at a higher altitude. So those are all things to consider. This is one of the really good papers that was done relating to aircraft design and reducing the impacts of global warming. And they called it global warming in 2011. Now they would say climate change, most likely. But if you take an airplane and design a commercial airplane to fly, and this is Mach number of 0.85, and this is the altitude it cruises at, 37,000 feet. And you want to change it, change the way it flies, and you change the airplane to be optimized to fly under different conditions. So if you change it to fly, instead of going Mach 0.85, you go Mach 0.78, then you've reduced the global warming of that by about 15%. And this is a cost function based on operating costs or something that we won't get into in detail, but if you fly slower, it may be more costly. If you burn less fuel, it'll cost you less. If you fly more slowly, you have to pay the pilot longer. All these things come into play. But in the model they use for cost, we could make that move, reduce the emissions, the global warming by 15%, and only increase the cost by less than 1%. And so that's the kind of trade-off that they're doing in this study. They continue to slow down the airplane and reduce its altitude. You get all the way down here where they're flying at 21,000 feet at Mach 0.714 instead of Mach 0.8 something, right? And they've only increased the cost in their modeling by 2%. That seems like relatively reasonable thing to do. Then they continue to try to push down the global warming effect of the airplane design by slowing down and changing the altitude. Eventually, it got to a point of diminishing returns where mostly all they did was increase the cost to fly the airplane. And you can see the airplane change shape. As it goes slower, the wing doesn't need to be swept, and some other things all come into play. But as an engineer looking at this, you look at kind of, we call that the knee in the curve. That's one of the good spots to start thinking about. So there are people thinking about what if we redesign airplanes to fly at 21,000 feet at Mach 0.7 instead of what we do today, which is about Mach 0.8 at 35 plus thousand feet. This includes the effect of you may be burning more fuel and putting out more carbon dioxide, but you're putting out fewer contrails and other effects. And so it attempts to include all those kinds of things. This is not necessarily the definitive answer. This is just a good study that traded off operating costs, airplane design, and global warming effects. So it's kind of one of the best studies that's been done in this area. One of the other activities, the other impact is the more traditional air pollution kinds of impacts of aviation emissions. So air pollution has a significant effect on human health. There's some debate if these people doing these studies are getting the magnitude right, but it's definitely a real effect. So it's more traditional air pollution that comes out of the engine. And a lot of it has to do with the people that live around airports, right? If you live near an airport and the wind is blowing in the right direction, you can smell jet fuel coming by you. You can, jet exhaust, those things all are, bad pollution. And so those have health effects. And it's pretty easy in some of these studies to come to the conclusion that many more people are killed and injured by air pollution from aviation than will ever be killed in crashes and things like that in airplanes. Like I said, people argue if these numbers have the right magnitude or not, but there definitely are effects relating to increased asthma, heart attacks, other traditional health effects that you get from air pollution. You can probably argue that cars and trucks produce more pollution and injure and kill more people than aviation. But these are still, like I said, much bigger numbers than people killed in all aviation accidents in a year. Right? So this is another reason to try to clean up our act, even though this doesn't have any direct impact on climate change. Okay, if you're going to attack CO2 emissions in commercial aircraft, you have to go after the airliners. Here's a chart that shows twin aisle. Those are the bigger airliners, right? The 787s and 777s. They put out about 57% of the CO2. The single aisle airplanes, the A320s, the 737s, are putting out 36%. The smaller regional airplanes, 5%. General aviation, business jets, military aircraft, those are all part of less than 1% wedges here and there. But the vast majority, 90% of the emissions are coming from commercial aircraft. So everyone should do their part. Nobody should make it worse. But until you have to address commercial aviation in order to make an effect on aviation's total impact. Okay, here's another version of that wedge chart. I don't know if there's anything that's necessarily different here. I'll just skip that one. One of the things you may hear about is carbon pricing. This is those offsets, right? Here they're shown in orange. How are we going to do some offsets? Around the world, they're starting to price carbon, and California has a system. I see South Africa has some taxes. South Korea has one of the most robust systems to look at this. So this allows, what they're allowing is passengers, when you book your flight, you can pay just a little bit extra, and you can now say that you'll buy an offset to offset the carbon dioxide from your trip. So those are things that are starting to happen. Industries are doing it. Okay, so just an exercise. You may hear numbers flying around. If one of the values that I've seen recently is $30 per ton of carbon, what is it? What additional cost is that on a gallon of jet fuel? And if you run through the calculations, it turns out that it's about 30 cents on a gallon of jet fuel. So $30 per ton. So it's $100 per ton of carbon is about $1 a gallon tax on jet fuel. And we're not at that level yet. So 30 cents isn't that big an impact. But in order to start changing the price of jet fuel, these carbon prices probably need to start. When they get higher, they'll have a bigger effect. But some of the things that you may see. And there's a lot of work on different tax credits, right? There's taxes and credits, and all these things are being worked in different ways. A lot of policy activities related to sustainable aviation fuel. So a lot of activity. The current administration is pretty prone to be working on these things, building these kinds of incentives into some of the Inflation Reduction Act and the other spending that they put out in the last 10 years. Okay. Let's talk a little bit about some of the technologies that we looked at. This is from one of the studies that we did for NASA. It's called Subsonic Ultra Green Aircraft Research. And we looked at defined baseline airplanes, right, in this 2005 timeframe, an improved version with new technology from the year 2030 to 2035. We looked at different wings and things like that. We looked at increasing the aerodynamic efficiency. We looked at different shapes. We looked at adding hybrid electric propulsion. And then we looked at even more advanced technologies that might be available in the year 2040 to 2050. So these are some of the things that we looked at. And we define these terms. N+3 is the time frame of 2030 to 2035. N was the time period of 2005. And then N+4 was 2040 to 2050. So you'll see us refer to that. But for some of the technologies beyond the N+3 technology, we looked at things like natural gas, liquefied natural gas. We looked at hybrid electric propulsion systems. We looked at advanced batteries. We looked at fuel cells. We looked at hydrogen. We looked at hybrids between fuel cells and batteries. We looked at fully electric airplanes to try to do some of these missions. And we've even looked at what you would do if you wanted to try to fly a nuclear reactor in an airplane, something that had been looked at during the Cold War. What would have to happen to make that practical? I won't be talking too much about that. It has to get very light and very safe before that can apply. We looked at some of these technologies in our different studies. We came up with these cute little names, like the Sugar Volt came from that, the Sugar High, the Sugar Freeze. Those are some of the different things we referred to. All right, so a little bit on fuel, on energy sources and what the current energy flow looks like. Here's the US energy consumption, and you can see the contributions of solar, nuclear, hydroelectric, wind, geothermal, natural gas, coal, biomass, petroleum, what goes into electricity generation, and what goes into residential, commercial, industrial, and transportation, which includes aircraft. So these are kind of fascinating graphics to look at. But we're going to pull into this stream. We're thinking of what if we can use some of this biomass produced. What if we put that into transportation? What can we do with it? It turns out though that everyone's going to want it. So the supply might be a problem. Because not only does aviation want it, but the shipping industry, cars, and trucks also want to use it to clean up their fuels as well. Okay. So a little bit on fuel. Some of you know more about this than I'll show here, but the fuels are all about, and let's review our chemistry a little bit. Hydrocarbon fuels are molecules that are mostly chains of carbon with hydrogen attached, and we'll see some of those. carbon is relatively heavy with an atomic weight of 12, and hydrogen is the lightest with an atomic weight of 1. And the energy you get by combusting one of these fuels, combining with oxygen, is you create hydrogen, you create water and CO2. That's what releases the heat. But the density of the fuel is about the total atomic weight of the atoms that form the molecules in the fuel. So things like jet fuel are on average C12, so a chain of 12 carbons with 24 hydrogens attached. You add that together, that has a weight that is much higher than hydrogen, which has 2 very light hydrogen molecules. And you'll see how that plays in all this. And methane is kind of in between. And yeah, right, hydrogen's the lightest, carbon is over here, very common, but much heavier, right? 12 times as heavy as hydrogen. And so when we look at, on this chart, we have different fuels here, and then we have the energy per weight of the different fuel. So, okay, so jet fuel, Jet A, we call it, has a value a little under 10,000 in these units. With methane, a little bit better. Hydrogen has a lot of energy and is very light, so divide energy per weight, it's almost 3 times as good as Jet A, so that seems good. And then, for reference, batteries are way down here and they barely show up. Batteries are really heavy for the amount of energy that they carry. Lower chart, though, is the energy divided by the volume. So how much space does this fuel take up? Well, here's where Jet A wins, right? Jet fuel and diesel is very similar. Gasoline is pretty similar. So those are all have a lot of energy contained in a small volume. So that's really good for many aspects of an airplane as well. Hydrogen, though, takes up is a lot lower here, so it takes up much more volume to carry the same amount of energy, about a factor of 3 worse. So it takes up 3 times the volume that Jet A would take up. And the batteries are split down here. So in deciding, we're trying to develop something for aviation, if you're moving toward hydrogen, hydrogen has good energy, but it's lightweight, but it takes up a lot of volume. So that has a lot of impacts to the aircraft. Some of the other things that play in this is hydrogen for aviation is most readily stored in the most dense form you can store it is as a liquid. And so it turns out hydrogen liquid is a cryogenic. It is very cold. So all your systems have to accommodate that. Natural gas in a similar way, it's liquefied in the same way. There are some limited applications of hydrogen as a compressed gas, but we'll talk a little bit about that also. But your fuel system is completely different if you go to one of these cryogenic fuels. You have to worry about the cold, you have to worry about leaks, many other aspects come into play that make it really, really complicated and challenging. Let me focus, though, first on biofuels and synthetic fuels. So sustainable aviation fuel is a definition that's come about, and what the sustainable part of it basically means you've done some kind of analysis or certification that it's obtained from a sustainable source. The biomaterials that go into it come from a sustainable source, and it's not like you're tearing down the rainforest to make this stuff. You're not causing more environmental harm in doing so, and that's the purpose of this. So okay, that's the definition. Okay, a little bit on the jet fuels we're talking about. Most jet fuel is in the form of a paraffin, which is this chain of carbons with hydrogen on it. If you played with the little molecule kits in your chemistry class, here's a picture of what that might look like. They can be arranged in a couple of different ways and wrapped around and different things. But generally, they look like this. Jet fuel is a mixture of many different molecules of different lengths and configurations. Some of jet fuel that is made from fossil fuel ends up being an aromatic, which is actually rings of carbons with hydrogens attached in different ways. So a lot of different kinds of molecules. It turns out these aromatics are some of the more polluting parts when you burn them, and the paraffins are cleaner. That's kind of what the molecules look like. Let's see if we get this one to play. We have to do 4 seconds with the ad. I don't want to play YouTube.
It's a historic occasion. The Virgin Atlantic 747 behind me will fly using a biofuel that will come as a surprise to many around the world. Well, we've had a wonderful day today. We wanted to prove that a biofuel flight could take place, that a plane could fly at 30,000 feet on biofuel. People have always said that would be impossible. That has happened. And it's an historic day. We've committed to putting 100% of the profits from our airlines and our train businesses into trying to develop clean fuels, because the globe is being destroyed, and we've got to do something about it. Biofuels is one possible answer. Biofuels do not emit carbon. So over the last 2 years, we've been trying to prove the skeptics wrong. The airline industry emits about 2% of the carbon, and the carbon.
All right. I mean, a couple things, right? That was the first biofuel flight in a commercial airliner. It had a small amount of biofuel made by a babasu nut and some other things in it. Richard Branson exaggerated the benefits in some ways. He misstated maybe one of the chemistry a little bit. Biofuels emit carbon because they are hydrocarbon fuels. When you burn them, you get carbon dioxide. We'll show though that the net carbon dioxide could be lower, much lower. So anyway, but another thing to note, in 2008, we started looking at this. Today, biofuels different fuels are approved to fly in airplanes blended 50% with jet fuel. But the amount of jet fuel that's being produced in this way is less than 1% of what's being used by quite a bit. It's taken all that time and we're still less than 1%. There are some major ramp-ups going on around the world to increase that number, but it's taking a long time to get this going. And you remember from the wedge chart how important growing that biofuel, sustainable aviation fuel piece of the wedge was. So it's quite a challenge in doing that. Okay, some of the different processes used to make different kinds of fuels. So we're talking about synthetic fuel. It can be done, you can use almost anything, coal, natural gas, biomass, plants, all kinds of things. You can essentially go through a Fischer-Tropsch process, they call it, and create a synthetic kerosene, which is kerosene is almost the same thing as jet fuel. So that's a path that you can use. You can use oil-based plants. You can take plants that have oil in them, and you can process the oil and turn it into a biojet fuel. So instead of using crude oil, you use a bio-derived oil, and those you can use that to make jet fuel. You can go through. I won't talk much about this. You can make an alcohol process. You can use ethanol and convert it into something that you can mix with gasoline. One of the problems with that is it doesn't take well to low temperatures that aviation needs, and the energy content is pretty low. So not many people are talking about using any kind of alcohol in aviation. The Fischer-Tropsch process is mostly about, think of really big refineries would have, you've got the towers, you have tanks, you have all this stuff. So it's processed in many ways. You're essentially making carbon monoxide and hydrogen, and you're combining them together into the fuel that you want. So it works. It's a well-proven process. It requires a lot of energy to do it. And so we'll look at some of the comparisons. You can make a fuel using this process. If you start with a biomass at the beginning, it's not nearly as bad. If you start with coal at the beginning, you're doing an environmental disaster, basically, if you're using coal to make some kind of jet fuel. The advantage of using some kind of sustainable fuel and a biomass is this, right? Typical petroleum-based jet fuel, you pull it out of the ground, you transport it, you refine it, you take it to the airport, you fly it. you emit CO2, and then all the energy used along the way to get it there essentially is more CO2 ended up being used. In a sustainable aviation kind of fuel, you start by absorbing CO2 from the atmosphere into the feedstock, into the biomass. Then you refine it and process it and fly it and you burn it and the CO2 comes out. But you can argue that, right, that it's a circular system and a lot of the CO2 gets absorbed again, maybe not the same CO2, right, but some in the whole world it doesn't make any difference. The inefficiencies of each of the processes, though, mean that your energy essentially is being used. It had to come from somewhere. So that could create CO2 itself. So it's impossible for this system, this cycle to be 100% efficient because all these steps have some inefficiency. But you have the potential, and the studies have shown you can use different processes maybe to get as much as 80% reduction in the life cycle CO2 by using a circular process like this. Here's some comparisons of different ways of producing jet fuel, CO2 emissions, Jet A at the bottom, using 1.0 for like 100%. These Fischer-Tropsch processes with coal are terrible. Natural gas is worse than jet fuel. The biomasses are the ones that have the potential to really improve it. One of the big issues with the biomass is how much do you need? Here's a graphic saying, what if we took the entire world use of jet fuel and we decided we wanted to use soybeans, the oil from soybeans to make the jet fuel. You planted an area with soybeans, you would need something the size of Europe, basically, in order to create enough oil to do this. Not practical. Get that idea? Whatever you're doing, you can't have people cutting down the rainforest in order to grow this stuff. So deforestation is a big deal. About 25% potentially of global warming comes from deforestation. You don't want that to happen, so you don't want to do anything that encourages that. Here's a study that if you include the burning down of the rainforest kind of thing, now your biojet fuel is now worse than some of the other methods, right? So you don't want to do that. We looked at here's a saltwater plant that you might use. You need something like the size of France. Still looks kind of tough. Another thing we looked at, algae. So algae is a way you grow it in water. Maybe you grow it in bad water. Maybe you grow it in wastewater or salt water. That seems pretty good. You can create this. You can refine it into sustainable fuel. Some of the studies showed if you had like offshore algae farms, you might be able to get by with an algae pond the size of Belgium to handle all of aviation, which is starting to get not quite as crazy, right? Obviously, you wouldn't put algae all over Belgium, but you would spread out around the world in different places, algae farms. So it's getting to be something that might be more practical. And so like I said, the analysis people have been doing are showing up to about 80% reduction in life cycle CO2, which is why people are interested in sustainable fuel.
Virgin Atlantic on Sunday carried out the world's first flight of a commercial aircraft powered with biofuel, consisting of coconut and babassu oil. Not to be outdone, Continental is fueling its planes with I can't believe it's not butter.
So it's pretty fun when you're working on technology in aerospace, and it ends up being a joke on Saturday Night Live. I consider that a highlight of my career. Okay. Current biofuel status. Multiple pathways have been already approved by the regulators for blending 50% with conventional jet fuel. The reason they're blending 50% is to make them backward compatible with all airplane exhaust, all airplane fuel systems without having to do any limitations. You'll see. Also, they don't have nearly enough to, like I said, it's less than 1%, so they don't have a problem with having too much of it. There's still problems with the supply of the biomass that goes into this. Algae is expensive, and crops, we have to worry, as we mentioned, about competition with water, and food, and land use. Saltwater plants, how are those working out? They're still having issues. One of the most promising areas is processing municipal waste. Instead of going into the landfill, it's going into jet fuel. There's significant activity in the Los Angeles area looking at that and around the world. The supplies are limited, but there's a fair amount of that. There's a high interest in using these biofuels in supersonic aircraft to reduce their environmental impact. They use so much fuel, they'd love to be able to claim that they're more environmentally friendly. And so this is some of the activities. LAX is one of the airports that has a fair amount of this sustainable aviation fuel from municipal waste. Actually goes into the tanks at LAX. United is involved with that. Every few weeks I see new contracts being announced, and as well as plans for expansion of the facilities to make this stuff. So I mean, people are working on it really hard for the reasons that we stated. There currently are, these processes are certified at these different levels. The abbreviations are crazy, like many things in aerospace, right? The acronyms kind of go crazy, but you can see that all these acronyms. But there are different processes that have been approved by the regulators around the world that it may be used. One of the new areas is an area called electrofuels. So this doesn't use biomass. It actually uses water and CO2 that it pulls from a source, either the atmosphere or an exhaust of a power plant or something like that. And they use renewable energy to drive the whole process. They use that Fischer-Tropsch process that I mentioned, which takes a lot of energy. But if you have sustainable, renewable energy, you have a supply of water, CO2 from, like I said, either the atmosphere or another source, you can make this fuel, and you can make what's called an electrofuel, which is another kind of fuel that would be sustainable. So that's a lot of activity going in this area. It doesn't need the biomass, right? People worried about the limitations of it. And people are starting to do experimentation and making these systems more efficient. The biggest issue is they use a lot of renewable energy in order to keep them environmentally friendly. Would we be better off using that renewable energy for something else instead, like the electrical grid directly? But that's another question. It was discussed in the May 2022 edition of Aerospace America. Had this on the cover, jet fuel from thin air. That's what they're talking about. Another big development, which took them, I don't know why it took them so long, but Boeing and Airbus now, all the new airplanes in 2030, why they had to wait so long, I'm not sure, will be compatible with 100% of the synthetic and this biofuel. So the sustainable fuel to be able to go in 100%. They won't need to mix them with conventional jet fuel at all. But that's coming. So that's a good development. Like I said, the supersonic folks are trying to be as green as they can. Here's a picture of a supersonic airplane. And this is a bank of collectors that are sucking CO2 from the atmosphere and turning it into that electrofuel jet fuel that I talked about before. But it turns out this company is out of business, I think, and there's still a few out there that are working. It's a whole other question for another day if you want to talk about how environmentally friendly are supersonic aircraft. The answer, not very, but it's complicated. If you want more information, GREET is a tool from the Department of Energy that's used in these life cycle modeling. And the Commercial Aviation Alternative Fuels Initiative is the one that's spearheaded getting a lot of these things approved, right? So they have a website that they've been going, for 15 years or so working on this technology. And they're a group that brings together all the regulators and the industry and academia together, so that they're a good source. Okay, we're getting close here. Let's see, in the area of biofuels, I think we're running out of time. We have to speed it up to get through hydrogen, I think, right? We're trying to finish it up as well for this segment. Okay, so I'm going to fill out part of this matrix as we work through it. Biofuels have reduced the opportunities, reduce life cycle CO2. They can drop into airplanes. I didn't really talk about it, but if you clean up the fuel, you may be able to reduce the contrail formation somewhat. So that's something, the benefit that might occur. Synthetic fuels basically have the same, like those electrofuels have the same benefits. The problem with the biofuels or the biomass supply, the cost of production can be high, and they're not fully compatible with older airplanes. That's why they require that mixing of 50-50. The synthetic fuels have similar issues. Production cost potentially is pretty high for those. And they need a source of sustainable electricity, right? To put all that energy in to make that fuel. Okay. All right, let's talk some about hydrogen. Everybody's talking about hydrogen, right? Everybody's excited about it. Lots of activity. Here's the molecule for hydrogen, right? Very simple. 2 small hydrogen atoms. That's what hydrogen looks like. You remember these charts? Hydrogen was great when you look at energy per weight, lousy if you look at energy per volume. Here's an old study that we did on an airplane. You took an airplane that carried 133 people, which is kind of small. You put a hydrogen tank in the front and the back. You can see how much of the fuselage is taken up by that. But the airplane can be lighter depending on this. So we did some studies with that. So the airplane would get bigger because it needs more volume. It wouldn't necessarily be heavier because the hydrogen is lighter than the jet fuel. The big advantage of hydrogen as a fuel is it has no carbon, right? So it produces no CO2, right? So that's great. It does produce twice as much water as jet fuel. So that gets back to all that discussion on contrails. Are contrails worse for a hydrogen-fueled airplane? And we don't actually know if they're worse or not. We're not sure. We know there's more water, but we're not sure if they're going to form more contrails, and people are trying to figure that out. Because we're burning it, we still have some other pollution. We have this NOx, which is NO, created in a combustor. We still have some of that has to be taken care of. But there's no CO, there's no unburned hydrocarbons. And hydrogen is very clean, right? So the advantages of hydrogen are, does it produce CO2? Can we deal with the water is the question. The chart from 2008, we talked about the advantages and challenges of hydrogen. The advantages are reduced emissions. That crude oil independent fuel was something we said back then. Depends on how you make the hydrogen, but usually it's made from crude oil. It can be used in fuel cells. The challenges being production of the hydrogen, new infrastructure needed at airports. Will passengers fly in a hydrogen-fueled airplane? We all look at the Hindenburg catching fire. Need larger fuel tanks, and contrails are kind of unknown. Some of the different airplane concepts that people came up with, as they looked at hydrogen, you can see here's one, right, with a big hydrogen tank on the top. Here's one with 4 and a half hydrogen tanks. Here's one where essentially had one fuselage carrying the tanks, hydrogen, the other fuselage carrying the passengers. Here's one with short range and big hydrogen tanks kind of hanging on the wings. So these are some of the things that people can look at. Hydrogen is only environmentally friendly if you make it with renewable energy. Most of hydrogen today is made with natural gas in a steam reforming process. The carbon from the natural gas turns into CO2 as you're making the hydrogen. So the hydrogen comes out without carbon, but you've emitted CO2 when you're making the hydrogen. That's the way most hydrogen is made today. You can make hydrogen with electrolysis. This one shows going through a nuclear power plant to drive renewable energy or a clean energy source to make the hydrogen. You get very low CO2 in the whole process. So so making hydrogen with renewable energy is the only way that makes hydrogen environmentally friendly. If you make it with natural gas, it's not. So you will see all kinds. They talk about colors of hydrogen. You'll see it's a rainbow of things. Black hydrogen is making hydrogen from coal. Oh my God, what a terrible idea! Don't do it. Gray is how most of it's made, steam reforming of natural gas. Green hydrogen is hydrogen made with electrolysis and renewable energy. That's really the only way to go. Blue hydrogen is something where they take the CO2 that's created during the gray hydrogen process and they sequester it, capture it somehow. And so that's another discussion that we could have. That's that's a way to try to keep the CO2 from escaping. Hydrogen, right? This is the issue with hydrogen, right? We know its density isn't very good, is that the tanks you carry the hydrogen in can actually weigh more than the hydrogen itself, right? It can weigh, depending on whether you're doing gaseous versus liquid, all these things. A compressed hydrogen tank is going to weigh 6 to 18 times as much as the hydrogen that you carry. A liquid hydrogen tank is at lower pressure, but it's very cold. It's unknown exactly how much that's going to weigh, but it may very well weigh as much or more than the hydrogen is carrying. So all those benefits of hydrogen being light go away if you have to put it in a tank that weighs a lot more than the hydrogen itself. And there are a couple other ways to carry hydrogen. But one of the things I've been tracking is the storage density. So hydrogen weight over the weight of the hydrogen plus the tank. So if it's 100%, that means the tank weighs nothing, and it's all hydrogen. And you know, 0 would mean you have a really heavy tank and have very little hydrogen on board. Right now, ground vehicles are somewhere less than 10% in this parameter, and they're fairly happy with that because it's not as important to them. Interestingly, large booster rockets and things like that are up here around 70, 80, or 90%, but many of them are only used one time, and they're also very large, and the tanks are very light. So there are ways to carry hydrogen in a very light way. The break-even point between jet fuel and hydrogen in this chart is about 35%, because jet fuel is usually just put into the wing of an airplane with a very little amount of weight added to make sure that it's sealed up. Very efficient way of carrying it. Hydrogen now has to have a tank to contain it. So if the weight of the tank plus the weight of the hydrogen to the amount of energy stored goes above the weight of the jet fuel that has a similar amount of energy, you get a crossover point. And that crossover point is here. So if your tank storage density, this efficiency is less than 35%, your hydrogen in a tank weighs more than the jet fuel that you would have used instead. So that means your airplane is going to get heavier, have less range, things like that. Many of the studies people are doing show that the tanks can be lighter, so the tank plus the hydrogen may be lighter than the jet fuel, and that would be a good thing. But nobody's flying large airplanes like this yet, so this is where the studies are going on. Not all the data points are up here, some of them are lower. So this is I'm tracking this to try to understand, where hydrogen is compared to jet fuel. Also, other ways to carry hydrogen, you carry it in other molecules like ammonia, metal hydride, different things like that. It's not clear that those are going to be a benefit, but there are other ways. Ammonia is NH4. You're carrying along a nitrogen it doesn't help, but you still have 4 hydrogens in there, and it packages more in a different way. So there's people looking at alternate ways of carrying hydrogen. Hydrogen has the potential, along with some of these other fuels, to be used in fuel cells. So I won't talk too much about fuel cells, but hydrogen is here with a high energy per weight, but a low energy density, right? So hydrogen like that, and jet fuel is over here, like we've shown in other plots. But these can all be used in different ways in fuel cells. A lot of people are trying to not burn hydrogen, put it through a fuel cell. One reason is they're still a lot better than batteries, which are down here in this corner. So a lot of people are trying to see if hydrogen plus a fuel cell would be better than carrying a lot of heavy batteries. What else? A study done in Europe had a lot of players talked about how to apply hydrogen and sustainable aviation fuel to different sizes of aircraft, different ranges of aircraft, and so there's some good stuff in here. They basically concluded that for a lot of these airplanes with a significant amount of the emissions, hydrogen would be a viable option to look at. It's worth mentioning infrastructure is important for everything that we've talked about. The aviation industry is very much conservative when it comes to infrastructure. There are thousands of airports spread around the world. If you know, most of them that are used for commercial aircraft and things, you can get jet fuel, be refueled. If you have to divert because of a problem, you land in another place, you get fuel. If you start changing to a different fuel, you now need to have that fuel at any airport that you might need to use. The benefits of biofuels and the sustainable aviation fuel is they can basically be combined in the same tanks that they're using today. So those are pretty popular way to go. Methane, natural gas, and hydrogen all require different tanks. You need a hydrogen tank storage farm, maybe even a plant to create hydrogen at an airport. You need a lot of things. So the infrastructure is a very big driver for these things. Okay. So let me kind of fill this out. Right, so we can fill these out before. I'm skipping methane for time. Hydrogen has no direct CO2 emissions. That's its advantage. It has reduced direct emissions, except for water. Some people argue with me about this, but when I put this together originally, I said you need new aircraft because the tanks are going to get big. There are other people that are trying to make a retrofit hydrogen approach, and you can do that, but you're going to have to take volume out of the cabin, for example. But you can retrofit with a performance drop. The challenge, making hydrogen in a sustainable way that doesn't produce a lot of CO2, and that you can make it competitive on cost, airport infrastructure. And we don't know yet about the contrail of hydrogen, so we'll have to see how that develops. Okay, and then this afternoon we're going to talk about electric and hydroelectric. If you want to stick around for that, we'll be talking about these, and we'll fill out the rest of this chart. So in the news items, I think I'll probably skip this one. There's a lot of activity, including local activity in the area of hydrogen aircraft. ZeroAvia is a company that has operations in a couple of different places, including the UK and California. And Universal Hydrogen also has a Southern California connection, another company working on hydrogen modules that be plugged into airplanes. Airbus has a lot of activities. They're looking at aircraft studies of larger airplanes with hydrogen. The UK is very Fly Zero's another activity going on. You can see they're putting hydrogen tanks in different places on airplanes and doing the airplane studies. There's a book that's come out. It's got some good content. It's not as complete as I would like, but on alternate sustainable aviation, there's some activity. There's quite a few chapters relating to describing that as intros. And then I think I'll wrap it up with this. Another thing that I've been looking at and others have been looking at is if we cannot get the climate under control and we need to do something to try to reduce the temperature, there are ways that aerospace can intervene in something called geoengineering. And a couple different ways. You could block incoming solar radiation, solar energy by using in-space reflectors to reduce the amount of energy hitting the Earth and reduce its temperature. And another approach is going up into the stratosphere and injecting aerosol particles that also do the same thing, reflect some of the energy back up out into space. So people are actually looking at this. It's fairly controversial, but it's another area that aerospace may end up playing in the global climate change. All right, and if none of that works, aerospace can still save us because we can blast off this planet and find another one somewhere. Aerospace will be needed to take us there. So hopefully we don't need to do that. And I think that's it. Okay. I will take some questions. We're also going to break for lunch. And Ken, what do you think?
Yeah, very good.
So then we open up for a few minutes of questions.
Yes, I think Mr. Chan mentioned something, and Mike Alpha, go ahead. Oh.
Yeah, from experience in working in the space systems during the NASA program, my major concern with hydrogen is not only with the infrastructure for just daily use at an airport, but just plumbing it on an airplane in a safe fashion, because hydrogen's cold enough that it can cryo pump and generate liquid oxygen out of the air, and which is the real explosive issue with hydrogen. I really struggle to understand how people can think they can get daily operations in an airport environment and a regular airplane environment of plumbing liquid hydrogen around an airplane.
I think that's a good concern. What do you think about hydrogen leakage also?
Well, yeah, I mean, just we can't get a rocket off the ground because we can't solve hydrogen leaks with a company, with an organization's been doing it for 70 years. But to think that it can be done on a mass scale in the environment that we currently have is basically, don't smoke on the tarmac and use grounding cables. I mean, that's the basic operational safety restrictions for Jet A right now. And to turn that into working a cryogenic fuel, especially a cryogenic fuel cold enough to liquefy air, is I don't see anybody working those issues. They're working about packaging, and making it more efficient, the things you talk about. But I never see anything about people working, how do you solve that problem?
I think that's fair. I think what they're being forced to do is they're flying demonstrators that have these systems in them. So they're being forced to address those issues. How successful they'll be, I guess we'll have to see. So I think they're taking the steps to look at them, but one issue is a lot of the work's being done, privately and in a proprietary way. So we're not seeing, it's not like we're not sharing necessarily all of the lessons learned, and we're not seeing all the results. They're probably hiding the poor results, right?
I can see a potential in a fuel cell for smaller airplanes, because you can package the hydrogen in with the, as a unit system, and to generate the electricity. But when you got a plummeted engines hanging on a wing, that's when things fall apart, in my view.
Okay. All right, that's good. All right, thanks.
Mr. Chan, do you want to say something? I saw you type something in the chat. Well, I guess not. So Paul is the person. Maybe they'll have more questions after lunch. So I think that we can call for the break.
Okay, let's do that. And we'll get. What time are we starting up again? We're starting at 1, right?
Yeah, 1. Yes.
Okay. All right. Pat.
This meeting is being recorded.
So he's asking about other alternative materials that you can make hydrogen tanks out of that will help make them lighter. And he asked a couple other questions, but yeah, definitely the biggest trade-off that people are doing with hydrogen tanks are in 2 different areas. One of them is they're comparing like a aluminum metal tank to a composite tank made out of composite materials, or wrapping a metal tank with a composite wrap around the outside to increase its strength, things like that. It's not clear that there's, which one is really lighter. It depends on application and different things. They're still working on that. The other area relating to hydrogen tanks is because they're cryogenic. We talked about that. They're cold. But as they absorb heat, the liquid turns into a gas, or it pressurizes and has to be vented out. So hydrogen tanks have insulation around them to eliminate or reduce the amount of heat that's absorbed into the tank. So they boil off, is what they call it, less. So the other area of materials technology being worked is what's the best way to put what's the best insulation material to use around the tank. And so there's conventional installations of different kinds, and then there's like vacuum jackets, like a thermos bottle kind of approach. And those are all kind of in the trade space of what people are looking at for hydrogen tanks. So you'll see composites, you'll see aluminum, you'll see different kinds of insulation, you'll see things that look like thermos bottles, and it's not clear, right? There's no clear winner as to what the best approach is. They're looking at that. Could be that small tanks will be this configuration, and as they get bigger, they might switch to different materials. But that's what's going on in terms of tanks. Okay. All right, I got 1 o'clock. Any other questions on the material this morning? Otherwise, I'm going to transition to the electric aircraft. Okay. Okay, so we're going to learn about current developments in electrified propulsion with emphasis on electric and hydroelectric aircraft. We'll show some design examples of aircraft of various sizes and missions. We'll look at different powertrain architectures, including electric, parallel hybrid, serial hybrids, combinations with combustion engines and fuel cells, and we'll talk about technology challenges. And you know, I showed this chart before. This morning, I'm showing it again, emphasizing these are the places where some of the electric aircraft stuff is going on, including the conferences coming up, the short course that we did in July, this batteries and fuel cell course that's starting in April. The sustainable aviation course won't have very much in it on electric aircraft because we have short courses on that already, so we don't need to repeat that material. And there is an Electrified Aircraft Technology Technical Committee of the AIAA. So if you're interested in that, you can send me a message or something and get involved in that committee if you wanted to work on the electrified aircraft activity. And let's see, I introduced myself this morning, so I think I'm going to skip this. Okay. So one of the interesting things in the electric aircraft space is that actually startup companies are doing a lot of the work, right? This is not, you know, traditionally a new airplane would be Boeing and Airbus and maybe a couple others that are doing it. All over the world, there are many, many companies looking at it. At least half the companies are startup companies that are working on different projects. The big aerospace companies are starting to invest, and they do their own thing, but they're also starting to invest in some of the smaller companies. So some of those kinds of things are going on. Also, you have things like a company like United Technologies, Pratt & Whitney, Rolls-Royce, actually have flying airplane projects because they want to do a demonstrator to demonstrate their propulsion technology. So they've got projects going. On the right, you see kind of a geographic breakdown, right? Basically, nearly half of all of the projects are going on in Europe, another half in the US and Canada, and then other parts of the world are actually starting to do more and more, but they're working on it too. So it's kind of a different, especially the small company aspect of this. There are many, many aircraft concepts and projects that have been worked on. The Vertical Flight Society keeps a database of all the different designs that they see among their members and people that are even not members of their organization. And from 2017, they're up to 600 different airplane configurations. Right? Certainly not all of them have flown. Some of them are just ideas or pictures or drawings, and some are variants on other ones. But just the idea that there are that many different types and looks of airplanes out there in the electric aircraft space makes it kind of There definitely will not be 600 distinct flying airplanes going into production. Many, many fewer now, of course, but it's just interesting. And we'll look at examples of some of the different configurations and powertrains. I could have used this in the previous lecture as well. This is the height curve. It's a height cycle curve. It's a generic curve for basically any new technology. And so you'll see the terminology is rather generic. It's not like only aerospace. But it's characterized by these different phases. Like they have cute little names: technology trigger, peak of inflated expectations, trough of disillusionment, slope of enlightenment, and plateau of productivity. And so technology starts out, the startup companies are formed, mass media hype begins, supplier proliferation, lots of suppliers, negative press, supplier consolidation and failures, venture capital funding, second and third rounds. Eventually, then you go through the trough of disillusionment and you start getting toward, well, what's really going to come out of this technology? Maybe this is over here. And so, where are electric aircraft these days? Well, they're definitely somewhere here near the peak. They may be at the point of supplier consolidation and failures. Somewhere over in here, I would say. It may vary some depending on how you look at it. But I mean, we're definitely not down here. We're definitely not over here yet. There aren't very many mass-produced vehicles in widespread use. So kind of, I think what I like to think I'm trying to do is to take us from this peak, sort of skip over some of this, and where ultimately could we end up if we address the challenges? What is it going to ultimately be like? I don't know. So, but talking about hype, I think, is a reasonable way to start a discussion about this electric aircraft space. There's a lot of hype, and let's try to understand what's important, and we'll go through that. Top level chart that Boeing produced when I was there. The benefits potentially for the environment: reduced noise and emissions, the ability to do unique configurations, and we'll see some of those, including things like distributed propulsion with multiple fans, urban air mobility, air taxis. Some of those things are easier or are enabled by electric propulsion. The ability to operate in a flexible way. You might have different power management schedules where you had low emission modes or quiet low noise modes or peak efficiency modes that you could operate at. Potential to reduce costs. By some calculations, the cost of electrical energy can be significantly lower than the cost of some of the fossil fuels. So there may be energy cost savings. There's the potential for maintenance to be lower. A mature electric propulsion system may not require as much maintenance as a gas turbine engine due to the fact that it has fewer moving parts, is less complex in that regard. So maintenance is often a result of experience, right? So you learn how to make things very reliable over time. So you may have a case where your electric system may have potential to be very reliable and low maintenance, but in its current technology without much experience, it isn't that reliable. So time is an experience. Challenges: the energy and the power density of the electric systems can be quite low compared to the gas turbine engines that are burning fuel. Safety issues exist. Dealing with high voltage, much higher than people are used to. Thermal management, keeping all the electrical components cool. And then also thermal management, the safety of the batteries. Some battery chemistries are prone to what's called thermal runaway, where they overheat, they catch fire, they may spread to adjacent cells of the battery, you might have a really big problem. So those are all issues that have to be, all challenges that have to be addressed. Ground operations are a big deal. Some people like to talk about swapping out batteries. You take a battery that's depleted, you plug in a charged battery in its place. I'm a little less optimistic about that than some people, but that's possible. And charging, right? You need to have an infrastructure at the airports. We talked about infrastructure before. Well, infrastructure, the charge is a big deal too. And then maybe, some people may not realize how involved it is to certify airplanes to fly, working with the FAA and the regulators around the world. It's a new technology. You not only have to develop the technology, you have to develop the process to prove the technology is safe, and then convince the regulators that's the process to follow and that you followed it. And so there's a lot of activities, many, many meetings, all kinds of stuff going on to develop the pathways to certify completely new power systems in airplanes. So that's a big deal. I don't find it as exciting as some of the other things that I talk about, but it's just as important in making the whole thing work is to figure out how you're going to get it approved to be certified. Okay, first goofy example. Okay, we have an airplane called the sugar-free. Remember, it came from that study we did with NASA. It's like a 737 airplane. Carries 154 passengers. Can fly 3,500 nautical miles on jet fuel. It weighs 185,000 pounds. It carries 60,000 pounds of fuel, of jet fuel. The jet fuel, Jet A, has lots of energy per weight. The units we're using here are units that make it easy to compare to batteries. 12,000 watt hours per kilogram. So that's 60,000 pounds. We're mixing metric in English units. It's horrendous, but we're doing that. 60,000 pounds of jet fuel has 325 million watt hours of energy. Sounds like a lot. If you use a really good lithium ion battery, it has about 300 watt hours per kilogram. So if you take 325 million watt hours and you divide by 300 watt hours per kilogram, you do that, it would take 2.4 million pounds of batteries to reach the same energy as 60,000 pounds of jet fuel. So that's the equivalent of 13 airplanes, the weight of 13 airplanes in just batteries to have enough energy to replace that 60,000 pounds of fuel. So you're not going to just take an airplane, take the fuel out, replace it with batteries, and call it a day. That is not going to work. You can get a little bit better. It's because the efficiency of an electric powertrain, as we'll see, can be better than the efficiency of burning jet fuel. But I mean, it might be twice or 3 times as good, but it isn't, 20 times as good, right? So that says you only need 1.2 million pounds of battery. That's still too much, right? So first goofy example, some people do this, get to this point, and they just walk away and say, oh, the airplanes are stupid. I hope in the end they're wrong. There are good applications for the electric airplane. So you have to do something besides just replace fuel with battery. Okay, an interesting chart that has different airplanes, ground vehicles, and even ships on it. The x-axis is the energy carried on board, and the y-axis is the maximum power that is used during a mission for that type of vehicle. And we have, it's a log scale, right, to read that, but what that means is vast orders of magnitude, right? Every one of these changes is an order of magnitude, right? Everything from little drones that you might fly, you buy and you fly around your house, the ones that You've used bother your neighbors down here. Some electric vertical takeoff and landing vehicles, and then some ground vehicles. A Prius uses this much power, carries this much energy. It's carrying the energy though, fuel mostly, right? Prius, it's not a plug-in Prius, right? It's getting all of its energy from the fuel. It's converting. There's a battery for like buffering and optimization. Tesla, right, is bigger. A large truck, oops, is over here. There's a Cessna 172 carrying fuel. It's here. King Air is a joint aviation airplane. S-92 is the helicopter. Q400 is a regional airplane. And then the airliners like the A320 or 737, C-17 transport, and the big A380, right, commercial transport. You can see very high levels in the upper right corner. Down here, these are like naval warships. They carry about, an A380 carries about as much fuel as an entire like destroyer warship. But the power level it's producing is more than an order of magnitude higher. So our airplanes use a lot of power, and they do carry a lot of fuel as well, a lot of energy needed. So, vast difference, right, between, you can make a small radio-controlled airplane and make it electric. That's one thing, but to make an airliner electric is a whole other thing. NASA's a great source for information on this. They have websites. The best thing about NASA is their goal, right, is to publish and share information. These small companies and even the larger ones that are developing these electric airplane projects, they're very secretive, they're very proprietary, very competitive. So you're not likely to get very much information out of them. They occasionally get a press release, video here and there, but there's not much of an incentive for them to release a lot of detailed information. So you're not going to find much in the public domain. But NASA they've got numerous activities going, test facilities, things like that. Similar activities in Europe going on. Right? Everything from very large airplanes to small general aviation airplanes, conventional takeoff and vertical takeoff kind of airplanes. So a lot of good information. You have to get a little bit familiar with like the power, the size of power, different things, right? And how much you would need. So a small 9-seat airplane might need 0.5 megawatts, we're going to talk about. Would use components that were 50 to 250 kilowatts each. Multiple ones together would add up to like a half a megawatt power. 19-seat regional airplane, or 19-seat commuter airplane might use 2 megawatts of total power. A regional airplane might use 3 to 12 megawatts of power. A 150-seat airliner might need 22 megawatts of power. And like a large airliner, right, with 300 seats might need something like 60 megawatts of power. I don't know, what is my car? My Chevrolet Volt uses 0.1 megawatts of power. Your house, probably something, right? Some fraction of a megawatt is what each house would probably use. So these are relatively big, and the timeline, there's a timeline across the top showing the development of the components. And most of the components you can get today, if you want to go to one of the companies developing the electric equipment for airplanes, the biggest you're going to be able to get is a megawatt. Electric motor that's a megawatt size. You can get 100 to 200 kilowatts. Those are relatively easy. You're going to pay a lot of money, and you're going to pay a premium to get a megawatt motor, but that's kind of what is available. People are studying going bigger, but that's kind of what they have. So at a megawatt, we could do potentially something like a 19-seat airplane with that. Or you could go a hybrid with a gas turbine or piston engine and do something bigger. Right? So a regional airplane could have 1 megawatt electric motor and then another a piston engine or a gas turbine burning fuel to cover the rest. So that's kind of where we're at until they develop bigger systems. What else? At some point, it may make sense to do superconducting, which we're not going to talk about in a lot of detail, but that's you can cryogenically cool electrical components, get them down to the point where they have very little resistance and very little heat is created and transferring energy around. Turns out that's very synergistic with, say, hydrogen, because hydrogen, we talked about it being cryogenic, you can use it to cool things down. Your MRI machine in the hospital is actually super cooled with, I don't know, helium or something, and it cools it down. They have big magnets in there with a lot of energy. So technology is kind of exists to do it. It's complicated. But, as you go to higher and higher sizes of power, that might come into play.
Mr. Bradley, does the wire change for superconductivity?
Yeah.
It does change? Okay.
The materials are different, and there's something out. Okay. Instead of a conducting copper wire, it's going to become a conduit that has cooling around it and a different material. Yeah. Okay. One of the things that electric airplane studies, a lot of them turn out like this. Let me kind of take you through it a little bit. So you have, this is generic, right? So we kind of go through it. You have, you're designing an airplane to carry a certain payload. So you fix that. And then you want to see how far it will go using different kinds of propulsion powertrain. And so here's a plot you come up with. A lot of studies end up looking like this in the end. So you can design an airplane, here's the range in miles, either 400, 500, 600, up to 900 for this particular airplane. And then this axis is the specific energy of the batteries. So how good are the batteries? It's watt hours per kilogram is a unit. We're going to use those over and over again. So, I mean, today's batteries are down here, pushing 300 at the most. Their plans, you'll see where they may be able to go quite a bit higher than that. But for this particular airplane that's listed in this study, they looked at all these different options, combinations of these, and they found that if you had a long range requirement and your batteries weren't that great, this zone always wants to be an airplane burning fuel. It doesn't make any sense. You can't do the mission if you're trying to do a battery alone. This upper corner says that you have a short range requirement and you have very good batteries. These are very good far future batteries. This corner is electric, battery electric airplane, can do missions like this. And in between, these are where the hybrids, where you have both a battery and a fuel burning engine of some kind, like in play. So a lot of, like I said, a lot of the results end up looking kind of like this, which tells you batteries, the better batteries get, the longer range will be practical with fully electric airplane. It also tells you, there's places where having a hybrid may be the best solution. All right, so some of the things that come up, some of these things kind of like, you talk to somebody in the industry about, or even not in the industry, about electric airplanes. One of the first things they say is they learned when they were in their aircraft performance class or something that, oh yeah, the fact that the airplane burns fuel as it flies means it gets lighter. So that's a big deal. And batteries, when you use the energy out of them, they don't get lighter. So that's a terrible thing in airplanes. Electric airplanes can never work because there's this effect. Well, yes, but it's not that big effect for a lot of airplanes. So like here's a 737 kind of airplane, and it goes from 100% weight to something like, it burns off about 25% of its weight in fuel. So it drops to 75% of what it took off. And if you look at that, it gave it about a 10% bonus in range because it got lighter. Or you burn 10% less fuel to fly the same distance because it got lighter as you flew. So that that's not a huge deal. And if you're flying shorter ranges, it has less of an effect. So the first argument that people make isn't really a very good one. There are other reasons why electric airplanes have a hard time, but this really isn't the biggest one. And you can look at this. These are the equations that we use. It's called the Breguet range equation. There are different forms of it. If you study aircraft design or performance, right, you study all this, but you don't need to be an expert in this to understand the basics. It says the range is equal to the energy of the fuel, which is energy per weight, the efficiency of the powertrain. This is the gravitational constant, which actually doesn't change unless you go to another planet. We're not going to do that today. Lift to drag ratio tells you how aerodynamically efficient the airplane is, right? So less drag, more lift is better. And then this complicated expression is what happens when you burn the fuel off. It's the effect of burning fuel over the mission. This is the conventional one, so we have fuel. The electric one is simpler because you're not changing the weight, so it just has all the same terms, except the last term is battery divided by total mass of the airplane, so the battery weight fraction. But I mean, there are different efficiencies and there's different energy. So obviously they're not the same, but you see the formulas. So that's really the math. Is this term over here, the logarithm of 1 over 1 minus m fuel over m, which comes from integrating the derivation of that Breguet range equation, which we're not going to go over. But so essentially, you can see that you can look at this mass fraction of fuel or battery, and then this is the value of this term. And so you can look at it more precisely mathematically. Some of the short-range aircraft, like Cessnas and things, they could lose 5 to 10% of their range because the weight didn't burn off. Long-range aircraft could be up to 20 to 25% of their range. So it's not a showstopper, but it is something that has to be considered. These different terms in the equation are important to think about because the range we're going to talk about is dependent directly and proportionally to the battery-specific energy, right? The E term. The efficiency of the powertrain, right? It's the system efficiency we're talking about, directly proportional to that. The aerodynamic efficiency, directly proportional to that. And in the last term, this M empty over M, and you have to include a payload too in there, is dependent on how lightweight you can make the structure. The interesting thing is, these are exactly the same problems that you have to address if you're designing a regular conventional airplane that burns fuel. These are all important in the same way. So it doesn't really change the way you design airplanes. It just has a few different trade-offs. Okay. When you're looking at how to design the powertrain, the power system, the propulsion system for an airplane, you can start out at the top level with choices of what kind of energy source to use. You use jet fuel. You can use cryogenic fuels like hydrogen or methane, or you can use batteries. You can have a gas turbine or internal combustion engine, and you can use a fuel cell, and you can see kind of some of these connectors over the dome. Like a conventional airplane burns jet fuel, goes through a turbine, uses a shaft to connect to a propulsor, which is a fan, which is ducted, hanging under the wing, and really doesn't do too much for lift. That's pretty much conventional airplane. You can also do various combinations. You can go these other pathways. You can use it. The turbine can drive a generator instead to generate electricity distributed by wires to an electric motor. You could have multiple electric motors connected to that. You can have propellers or open fans instead of ducted fans. So these are the kinds of decisions that you make along the way. designing an airplane, and you're designing it to meet the requirements your customers have, and so you pick these different choices. And you can go through these and kind of their advantages and history behind the choices that have been made. For example, jet fuel, we saw before, high energy per weight, high specific energy. There's existing worldwide infrastructure. It's great. The challenges of jet fuel are, interestingly, crash safety, right? Jet fuel is inherently quite dangerous to work with. Aviation is so safe, not because jet fuel is a safe fuel necessarily, but because we were so practiced and experienced at making airplanes, fuel systems, and things like that safe. We've worked at it since the Wright brothers, and airplanes are very safe, but they're safe because we worked it so hard. Carbon footprint, we talked about how sustainable jet fuel was, and at times, jet fuel is very susceptible to the supply of oil and global supply disruptions. So periodically that comes up as a major consideration. And the other fuels, we talked about the hydrogen as a fuel and its advantages and challenges. Batteries, the biggest problem with batteries being, right, they're so heavy for the amount of energy they carry, they have other issues. Okay, so pluses and minuses, and history, right, of why people decided these things. We'll talk about a couple of these. Batteries if you charge them, they need to have a renewable energy source. Otherwise, they're not environmentally friendly. There are also issues with making and recycling batteries. We'll talk about it some length. What else is mentioning? There are electric haters out there. There are people that hate electric cars. They're being stoked by politics sometimes, right? So we're not going to address all those kinds of things, but you have to watch out. There are many studies, there are many headlines that say electric, battery, whatever, are terrible for the environment. Most of them are exaggerated. They're not all exaggerated, but some of them are. Many of them are. So, it's good to dig into the details. Why are they saying that the batteries are so bad? There's probably some truth to it, but sometimes there's not. So you have to watch out for that. Okay, so turbines, also internal combustion engines, gas, different engines. They don't have to be a big aviation gas turbine, some kind of fuel burning engine. And then fuel cells. We started talking a little about fuel cells. We'll talk more. Here we go. Fuel cells. What is in a fuel cell? Well, a fuel cell inherently is hydrogen goes in one side of a fuel cell, oxygen goes in, and out comes water and electric power, right? So that's good. And so a lot of people are interested in fuel cells because they create that electric power and they can use hydrogen and things. There's several kinds of fuel cells, at least 3 very common kinds, and even more than that. But most fuel cells love hydrogen, take in oxygen, and do this. If you start out with something like methane, CH4, you have another component that has to go into the whole system. It's called a reformer, sort of a little refinery that separates the carbon from the hydrogen. And the hydrogen goes into the fuel cell loves hydrogen, that works. But as a byproduct, you're getting CO2. So if you have a fuel cell, but you're using a hydrocarbon fuel with a carbon in it, you're going to create some CO2 as well. So gotta watch out for that. And if you start with, say, conventional jet fuel, you need more steps in here. You have to do things like make sure you don't have the sulfur in it. Your reformer has to do even more to break the molecules apart. And so hydrogen is the best thing to use in a fuel cell, but you can use other fuels as well, but you have to put in essentially additional equipment and steps in order to make it work. So, and we showed this chart before, but I didn't talk about it too much. But you can see all the different fuels. These will all work in a fuel cell. Natural gas, propane, gasoline, diesel, jet fuel, liquid hydrogen, compressed hydrogen, alcohols will all work in fuel cells. Batteries, like I said, right down here. You can use the hydrogen in two ways. You can burn it and run it through a fuel cell. I did a paper this summer talking about fuel cell hybrid architectures, how many ways you might combine fuel cells with gas turbines and batteries in a propulsion system for an airplane. So we looked at some of those. There's no real earth-shattering developments in there. It's more of a catalog of different architectures. NASA has put this together for, in general, electric propulsion system architectures. And this chart has been used many, many times. It originally was inspired by what are the car companies doing with their hybrid powertrains and things. And so this is the aviation version of that. And so you'll find things, pretty simple. Like all electric or pure electric or universally electric is the terminology they use. A battery is connected to a motor that drives one or more motors that drives one or more fans. And they could be propellers, we say fan, but it could be propellers as well. So that one, pretty simple, right? Turbo electric is yet another one where you use fuel to go into an engine that turns a shaft that drives a generator that is then distributed to one or more motors and fans, and that's called a turbo electric architecture. No battery, right? No energy storage. A variant of that is the series hybrid, where there's also a battery. So you can decide and use the battery to supplement what's coming out of the generator, or vice versa, different way of doing it. A parallel hybrid is one where it's more like you have a jet engine it's turning a fan. Looks pretty much like a conventional engine, but you supplement it with an electric motor on the shaft, or one or more of the shafts of the engine, and you use a battery to drive the electric motor. And that's what a parallel hybrid looks like. And there's a couple others. There's a series parallel partial hybrid, which basically combines everything. And there's a partial turbo electric. It's a little bit variant on that. So these are the terminology used for different architectures. And we're going to do a few kind of sample calculations to see what these things look like. So we talked, remember that powertrain efficiency was one of the parameters in our equation for range, right? So we're going to track that a little carefully. So across the top is a conventional airplane propulsion system, which we're saying is a turbine engine. And we're saying the efficiency of the turbine engine converting fuel into shaft power is about 50%. And the number varies actually a lot. Small engines have a lower number, and this is maybe the biggest engine on an airplane or in a power plant might be able to get up to 55 or 60%. It's like a thermodynamic efficiency, but 50% is what we're going to use here. Might be applicable to a small, medium-sized airliner engine, 50%. Gearbox to match the speed of the fan to optimize its aerodynamics. Many new engines have gearboxes, not all of them, but 99%, very efficient. And then the propulsor, which in this case like a fan or a propeller, is about something on the order of 80% efficient, right? Maybe a propeller operating at low speed with variable pitch might be a little higher than that. It could vary some, but we're going to use 80%. And if you multiply those together, you get about 40%. So powertrain efficiency that we plug in that equation for conventional medium-sized airliner might be 40%, which isn't too bad. But if we have this electric architecture, got this battery, and there's some kind of losses associated with the battery discharge and the controlling of the battery, so we'll put 99% there. We've got some wires running from the battery to the electric motor. It's about 99% efficient. There's a motor controller. Sometimes called a motor drive, different terminology, but typically they're at something like 95% efficient. And then the motor itself is about 95% efficient. Likely to have a gearbox, and if we put the same propulsor on the end of it, we'll use 80%. So if you multiply these numbers together, you get something like 70%. So in our example, our electric powertrain is a little less than twice as efficient as this one here. You might ask, we didn't include all the efficiencies you could think about. For example, we didn't include anything in here about pulling the oil out of the ground and refining it and sending it to the airport and putting it in the tank. We didn't include that. And on this side, for the electric airplane, we didn't include generating the electric power, running it over the grid, and then charging the battery. So we didn't include those pieces. So you can include those pieces also in your efficiency analysis. You don't need to include them in the range of the airplane, but you need to include them in the overall evaluation, potentially, of the airplane. But look what happened if we switch to this turbo-electric architecture. What else should I say? The question here is, we've added all these like round boxes here. We didn't have the turbine engine, so we don't have that weight, but we have the battery. So it's not clear, which one of these is really heavier. We haven't come up with an example that's defined enough that we can do that comparison. But the batteries tend to be pretty heavy, so we want to balance that. Turbo-electric system, we can do a direct comparison. Here's our conventional airplane propulsion system. And here's our turbo-electric system, where turbine engine drives a generator. It goes through a controller, distributed on wires, to a motor drive, to a motor, to a gearbox, to a propulsor. Multiply those out, we're at 32% to do the same thing that we did at 40% here. And we have these three components in blue, but we've added these 5 in the middle. So obviously, this turbo-electric architecture has lower efficiency and more weight. And so why would you do a turbo-electric system? Well, it has to be some other reason besides pure efficiency or weight going after. So we'll see some options about why you might want to do that. Parallel hybrids, right? A lot of activity. Some of the stuff that I did for NASA was these parallel hybrids. They look kind of like this. A turbine engine driving a gearbox that combines 2 different power inputs as a propulsor. So it's a combination of what we showed before, 39% efficient across the top with a conventional turbine burning fuel, 69% across the bottom with this battery supplement to the system. What we do have is more flexibility to improve the system, because instead of just having a battery for all of our energy, we can use fuel on long-range missions using this top part of the powertrain to achieve the longest ranges that we need. And on short-range missions, maybe we can run more on the battery side and have fewer emissions. Airplanes have to carry a lot of reserve energy for divert in case of weather or problems, and so that is just kind of dead weight. If we use fuel instead of batteries to carry that energy, we can save weight in the system. So that's another reason why the parallel might look good. Because we have this supplemental power, we can actually potentially reduce the size of the turbine, because it only needs high power for takeoff, for example. We can use the battery to supplement the power, so we can make the turbine smaller. That might have some advantages. We can operate the turbine engine at its most efficient speed and things like that, and get a little bit more performance out of it. So maybe that save some fuel doing that. What else can we do? If we run this right, we can actually make this motor into a motor generator. You can reverse the electrical wiring essentially on a motor, and it can function as a generator if you design it to do that. So that's interesting. You use that to recharge the battery. So you actually run the energy backwards through here to charge the battery. Might be good. So there's different, it's flexible, but we haven't proven, right, that it's better. It's proven that there's more flexibility. And you can run the hybrid, the parallel hybrids in different modes. Call this a mild hybrid where the electric system assists. I mentioned, if you're flying long range, you just don't even run this side at all. You reduce the amount of batteries you carry, maybe use more fuel, use this side. In this case, you have designed it so you can actually shut off the turbine engine completely and run, say, just the cruise part of the flight on the battery. And you wouldn't be making any contrails. You don't have any emission. Maybe some reasons to do that. You might want to be quiet. What else can you do? This is kind of a different application. Because you've electrified everything, you can run the turbine. The turbine can run a generator, which then generates a bunch of power, which you can use for high power systems. So if you're on a military mission and you want to, I don't know, power a laser beam as you're flying over somewhere, and you need a ton of power to do that, you can use an architecture like this, potentially, to do that. So these are some reasons why, even if it was heavier, you might want to have an architecture to do some of these things. The partial turboelectric architecture, what you can do is once you generate electric power, you can then distribute it to multiple propulsors on the airplane. I'm going to show you what that is. So that's called distributed propulsion. So this kind of system lends itself to doing distributed propulsion with a bunch of different fans instead of only a couple. We can do a quick evaluation of some of these things. The ways to do these distributed propulsion options with multiple fans. The turbine engine can do it. If you design a bunch of shafts to distribute the power with mechanically turning shafts, that's been done. And one turbine engine can drive 3 separate fans or propellers, for example. One reason that might work is if you can distribute the propulsion and get them to be more efficient. We'll talk a little bit more about that, but that's one reason you might want to do it. If you can make the propulsors, the fans, more efficient than one big one, make 3 small ones more efficient, then you can actually get a bit of a performance advantage. 42%, we had 40 before old architecture. So maybe there's a bit of it, so you could do there. You could also do the same thing with 3 small turbines instead of 1 big one, for example, like smaller ones. The problem you get into is the turbines get less efficient as you make them smaller. So one reason why airliners have 2 big engines instead of 4 engines is one reason is because the bigger ones can be made more efficient as you scale up all the components. These are the kinds of things that we look at in what we call propulsion integration, where we look at how you combine the propulsion system with the airplane, the aerodynamics. You go to, so there's a bunch of different possibilities, distributing the propellers and fans along the wing. You may be able to make the wing smaller, or keep the wing the same size, and you can blow the flaps to make them more efficient, to get more lift. And so, like this is the Electra airplane that I've been working on one company. You get very short takeoff and landing because we are blowing the wing with all these distributed electric motors. Also, a lot of the vertical takeoff companies that are doing these air taxis, they have all these different vertical takeoff motors. They either rotate or the wing rotates and take off vertically. They're able to distribute the power around to all these different propellers, and that's one of the ways that they make those systems work safely. And so they rely on the distributed electric propulsion in some way to do that. Hydroelectric propulsion in airliners. It's shown that kind of the big airplanes, there's a potential efficiency improvement of 0 to 5%, depending on the studies that are done. So taking an airliner and making it a hybrid electric propulsion airliner. Some of the smaller, the turboshaft engines in the regional jets are able to take advantage of a little bit more. They're actually showing in studies 5 to 20% improvements in, say, fuel efficiency by going to hybrid electric propulsion. So those are things that you'll see the big engine companies working on. And then boundary layer ingestion is something where you put the fans in the back of the fuselage where they capture the boundary layer. It's counterintuitive and kind of hard to get the whole thing to make a whole lot of sense, but essentially what you're doing is you're adding power at a lower velocity, generating the same amount of thrust, but you need less power because you're doing it at a lower velocity. So it's a little hard to explain, but there are people that are showing benefits to that, anywhere from 0 to 10%, different studies and tests and things that they've been doing. So these kinds of propulsion integration things are made, some of them are made possible by the idea of doing these electrified propulsion systems. One way that you can actually get better efficiency in your fan, for example, is by making them bigger and bigger and capturing more air. What this shows is the efficiency of the fan system is a function of the velocity increment that you're giving the flow that comes through the engine. So it's more efficient to take a bunch of air and give it a small change in velocity than it is to take a little bit of air coming in and give it a big change in velocity. Even to generate the same amount of thrust, you can do it more efficiently with a bigger amount of air, a bigger fan. That's why the fans on airliners keep getting bigger and bigger and bigger. Is because they're taking advantage of this efficiency. And so that's 5 to 10% kind of efficiency that you can gain by doing those kinds of things. And that's why the engines keep getting bigger. The fans on the engines keep getting bigger. And so you can also get the same efficiency improvement if you have more fans, if the total area of flow that you're capturing goes up. It may be very hard to fit one really big fan under the wing of an engine under the wing of an airplane without scraping on the ground, but you might be able to get two smaller ones that have the same area underneath that wing, right? So those are integration. So that's one reason. Another reason people are looking at some of these potential architectures. One of the popular ones is turbo-electric distributed propulsion. Maybe we did turbo-electric before, but this one uses electrical wires, right, to distribute to a bunch of different electric motors that might be arrayed across there. Remember, the problem is all these extra components, weight, efficiency that you add in here. And so this can only look better as if you're getting some gain in propulsion efficiency. So you have to do something to get better propulsion efficiency to justify the extra weight and complexity and efficiency of your losses that you have. Okay. So a couple of exercises related to that. So just a little bit more precisely what we looked at before. Here's the turbo-electric architecture. Across the top, so it's 39.6% efficient. The bottom is about 31.9% efficient. That's the answer to the first part. How's it? Let's compare. This is a question of how much better would the propulsor need to be to have the same efficiency at the top and the bottom? So remember, we're chasing better propulsion efficiency, or better fan efficiency over here, propulsor efficiency. Turns out you have to have 99% in order to match what we have this up here, which is pretty hard to do. Not quite impossible, but that seems pretty hard. If, on the other hand, we could improve the efficiency of these components to 99% instead of 95%, the break-even point becomes 84% in propulsor efficiency. So we go from 80 to 84, we've made up for this efficiency loss. We still haven't necessarily made up for the weight, so that's a separate calculation. Now, another point to make, think about this, is everything that isn't 100% here, 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 is actually inefficiency, and it's waste heat, most likely. So, the gas turbine engine, when it burns, it's only 50% efficient. I said that. Well, the waste heat is in the flow that you just burned, and it goes out the back. And it gets the heat away from the engine and the airplane. You have to cool it, and there's things you have to do, but that's the main thing it does. It gets the waste out. the gearbox, right, it's 99% efficient, but that heat has to be taken out by circulating oil through the gearbox. And it comes out, and then the oil has to somehow exchange heat with something to cool it to make that system work. So it's much harder to get rid of the 1% from the gearbox than it is to get rid of 50% from the combustor from the turbine. And the fan efficiency, that goes into weight. So our electric system has a gearbox, but it also has all these 5%, 1%, 5%, 5% losses. And you have to do something with all that heat. And so that's a big deal. If you add that up, this one has 22 times the amount of waste heat that this one has. Really all these factors. And so some of the early studies were done and didn't take this into account. So what you need to do, you need to take that into account. So all the new studies that are done, people are having to worry about it, is what to do with all of the waste heat that comes from it. So that could be cooling loops and all these components. Right? Maybe it's, maybe the wire doesn't need to be cooled. It's not, it's spread out a lot. Maybe it's okay, but these electric controllers and the generators and motors have to be. I'm going to skip these. We went through these notionally before, the comparison of the direct connect shafted to the separate turbines to the distributed propulsion. So shafting, I'll go very quickly. Shafting works nicely, but you can only do a few motors on it, and it does add complexity because you need gearboxes and shafts. One of the big problems they had is they wanted to put these propellers on a wing, and then the wings, they all flex. So you've got these shafts with all this power having to be distributed off to be designed to move and bend with the wing. It's very complicated. So that's one reason why you can't do too much of that. Smaller turbines, right, led to lower efficiency. And then this can route, this has a lot of routing with electrical wires, so you have to do that. But it does work, but you have to watch the losses. Okay. The equation that we talked about, this is the, anybody like the integrals? No, nobody likes integrals. But this is the way that the range equation starts with the integral here. This is where that logarithm comes from by doing the integration. We showed a version of that before. All right, so we saw these. We worked our way through these, discussed the different terms. You can solve that equation in a little different way. M is the mass of the airplane. Pax is the term they use for passengers, so number of passengers times the weight of the passenger. You can solve the equation right in this form and look at doing different things with it. Okay, so you can take this equation and you can actually determine that for a combination of range, this will use 500 kilometers and 180 watt-hours per kilogram for the batteries, 70% efficiency. The lift to drag ratio of the airplane, to make any of these work, to achieve this range with these assumptions, has to be at least like 22. It's pretty high. So there are many combinations of range and payload and efficiency that you cannot actually meet, depending on what you're able to do for efficiency. And so you can check some of the claims that people make about range and payload and all these different things by just using a very simple equation like this. Okay, so we're going to do an example with, I like these numbers a little better, 300 watt-hours per kilogram for the batteries, lift to drag of 15, 70% efficiency of the powertrain, 20% battery mass fraction, 55% empty weight fraction. So that's the amount of weight you can add, and 1,000 kilograms of payload. So we're going to do some calculation. Found this online. You can go click on this. You can plug in the numbers, hit the button, and it will tell you the answer. For those combinations, the range is 231 kilometers. Right? Plug those in, you get 231 kilometers. which is 144 miles. Let's see if we can recreate that using our equation. So you do this, here's our equation for range, plug in 300, 9.8, that's the gravitational constant of Earth, 0.7, the efficiency, 15 L over D, and 0.2 for battery fraction, battery over total. And you get 64.3. Yes?
So this formula had logarithmic components for the mass. Is it gone here or?
The one, yeah, the one, that was the one if you burned off fuel
Oh,
and the weight changed.
all right, all right.
The weight doesn't change, it just comes out, just a simple ratio. Yeah. So it's easier, right, for this.
What's the empty mass fraction consist of?
Everything except the payload and the battery.
Okay.
In this case, yeah. Okay, 64.3 is not 231, which is what we think the answer is. Why? Because units are crazy. Even though these are what, SI units, these are metric units, we still have something we got to figure out. So what do we got in here? Well, we have a watt is a Newton meter per second. Maybe that's important. The gravitational constant is 9.8 meters per second squared, but that also can be written, it has to be written 9.8 newtons per kilogram in order to cancel out the units and give you the answer that you want. What else? Oh, we had hours in here because we had watt hours per kilogram. So we have to convert the hours to seconds. And then we have kilometers, but we had meters. So we have to get meters and kilometers. We got to get that conversion done. So even our simple example using metric units required us to do a little bit of thinking to make sure that we get the units right. And this is just, an example of this is what aerospace engineering is all about, is getting the units right and getting these things to come out. It happens all the time. We spend a lot of our time just trying to get the units right on all the numbers that we do. And it doesn't help that we mix English and metric and all these things. Here's a couple of equations that are useful in relating power to thrust. So essentially, right, power is thrust times velocity, a few things like that. And then unit conversions, if you talk about power, you got foot-pounds, you got watts, you got horsepower, all these things. You'll find the specifications for something in one set of units, and you need to use another set of units, right, to do your calculations. And even metric units can get confusing. You need to get the units to cancel out, even then you need sometimes to do some of these things. So it's way harder in the English units, but it's still hard in metric, and it's most hard when you're mixing them together. And that's kind of what happens when you bring the aerospace industry and the electrical component people, electric industry together. You've got a mixture of units all of them. So some of you probably are nodding your head like yes, these units drive us crazy.
It was going to be a real tricky.
Oh, and for students, it's terrible, right? The students, it's sometimes hit and miss, right? Just randomly substituting in conversion factors, trying to get an answer. It's hard. Okay. So, okay, we plug in our assumptions for the airplane in this equation, and it comes out as 4,000 kilograms. It carries 1,000 kilograms of payload, and 20% of the weight of this battery. So we got to make sure we get our units in there. There are conversions, right, between seconds and hours, and kilometers and meters. When you look at, if you took the payload out, replaced it with battery, what could you get? What would the range change to? And you can do those calculations using something as simple as this. And 520 kilometers if you didn't have carrying passengers. Okay, so that's the kind of example that once you have a sample, you can then change. Look at other examples. Once you got the units right in your sample, you can plug in different numbers and answers that you might want. Okay, this one is about the battery. We talk about batteries, and I've been using one number, watt hours per kilogram, right? They're more, but that's an important number. But what does that really mean? Well, often that is a single cell of a battery has so many watt hours per kilogram. But you have to combine it into a different package, into a module, into a true battery that you could actually put into an airplane. So you have to add weight and pieces to that, and so the weight's going to go up, so the watt hours per kilogram is going to go down. And then other factors that we haven't talked about is you can't use, if you're familiar with batteries, typically you don't use all of the energy out of the battery. You actually save often the top and the bottom part of the battery you don't use in terms of its charging ability, because you want to protect the life of the battery. You want to get a number of cycles out of it. You don't want to drain it completely every time. And usually, whether you know it or not, your computer and your phone are probably limiting how much of it you drain the battery to some level. You may not even know it, but it's doing that. So that battery might be 200 watt hours per kilogram, but if you're only using 80% of that energy, then it's not 200 anymore, right? It's only like 160 watt hours per kilogram if you're actually using it. And then what else you have to worry about? Batteries don't like to be cold, and they don't like to be hot. So if the battery is outside the range, it can actually have less, it can overheat, but also can have less power, less energy available to you as well. Question?
Good question. Are they normally charged really up to 100%, or they're just a little bit below?
It's pretty typical to be 10% low.
Lower?
Yeah.
It's like 90%?
Yeah.
Yeah.
I mean, there are exceptions, and part of it may have to do with time. It's like if you have a charging cycle where you reduce the charging rate toward the end, you can kind of sneak up on it more easily. But yeah, there's a lot of that goes on that we can think about. What else? Oh, batteries, as you use them, right, they have a certain number of cycles that they have a lifetime of up and down cycles. They tend to degrade slowly with time. And so you're doing your aircraft assumptions. Are you assuming you have a brand new battery on day one? Or are you assuming that's the battery the day before you take it out of the airplane and send it to the recycling center? And so what do you design your airplane to? An old battery, it's only 80% as good as it was when it was new, or do you design it to the battery the first day you have it? The answer is you shouldn't design the brand new battery. So what are you going to do? So that can affect how much battery energy that you have. And then I haven't talked about it because it gets fairly complicated, but the batteries are limited in how much power they can put out. So how fast can they get the energy out? And how fast can you charge the battery? And that affects the design of the battery as well. And also changes the losses and the efficiency. And so that's something, I'm not going to explain to you how to design for that. It's pretty hard, but that's another consideration. Your battery might be sized by the amount of power it needs at one point in the mission. If you need a lot of power for takeoff or something, that might size the battery instead of the amount of energy that you need. So you got to look at that. And then cost. Do you put the most expensive materials in the battery? Are you trying to get the cost down? So inside this battery system, there's a whole bunch of trades, right? And a whole bunch of requirements that have to be met. So it's very interesting design problem, right? The battery itself is quite a design. Okay, the projections for batteries improving over time. This is important, right? Because our batteries are not very good right now. They're better than they were, but they're improving at some rate that we don't quite know. But in the future, how good can they get? Here's some estimates from the Department of Energy and NASA workshop that we had in 2019. So they're saying on this left side, we have the cell-specific energy, and on the right side, we have the pack-specific energy. So that's when we go from the cell to putting it in a battery pack. The numbers on the right are lower than the batteries on the left. So that's what that is. But what we see, these are different technologies and chemistries, materials mostly, in batteries that they're working on developing.
and they're getting, they're more and more far out as you go from left to right. These are the potential of taking a 300 watt-hour per kilogram battery today and turning it into something that's 400 or 500 in the future is shown on this chart. These are still lithium batteries, lithium batteries that we hear about mostly today. But you can see a different material type. This is a lithium metal sulfur version, so different materials. These are called solid state batteries that don't have any liquid in them. It's a different way of putting a battery together, and they're working on these, right? So there's some possibilities there. Today they're under 300, not very practical to manufacture them yet, but they're working on these. And there's some potential to go to higher levels. Some other concepts that might be able to get to 500 or higher. So here's some metal, either lithium, magnesium, aluminum air batteries, where they actually bring in oxygen from the air, which is starting to look a lot like a fuel cell that we talked about before, but it's a battery concept. Some lithium sulfur chemistries, and this is a flow battery, which is essentially operating very much like a fuel cell. So there's some potential to get to 500. The question is how long it will take them to get to 500, and what's the potential to go beyond 500? And those are still real open questions. Other people look at other ways of doing something innovative with batteries. Here's a concept where you essentially turn the wing into a battery by having one surface of the wing be an anode and the other a cathode. And so those would be called multifunctional structure or structurally integrated battery concepts. So people are thinking about that. But kind of as an example, here's what happens to that specific energy. If you had a 400 watt-hours per kilogram cell uninstalled, and you take 25% weight to put it into a battery pack, you only use 80% of the cycle of the energy on board. You say, well, I'm going to assume the battery's degraded 10% due to storage or due to use, not as good as 10% worse than it was when it was brand new. And these on the writers, or if your airplane had to have a reserve that you didn't want to spend. So we'll calculate that a little more rigorously later, but it can drop down. But you can see we went from 400 down to a little more than 200 to get here. And then if we actually have to start tracking reserve energy for the airplane, the amount that we can use to actually fly a mission might be more like 100 instead of 400. If we started out at 200, we might end up at 0, have no range that we could fly the airplane. If we improve to 600 at some point in the future, we might end up with over 300. So by the time you take into account all these, we call them knockdown factors, the batteries aren't giving us the ranges that we like. Here's an example that we use in the class to go through, to generate the numbers that you saw previously. So we go through these. So it's a 2,200 pound, 1,000 kilogram airplane, real smaller than one we looked at before. And these are the numbers in there. So I'm going to go through, essentially what I just showed you, these different factors. So if we start out our airplane, we're using 221 watt-hour per kilogram batteries, which is what NASA was using in one of their demonstrators. And you calculate the range, it's 326 kilometers, which is a pretty good range. That's a pretty fun airplane. You can do a lot. If you did the airplane, you made it fuel burning, you could probably fly farther than that. This is 326 kilometers is a pretty nice range for an airplane, for like a general aviation airplane, kind of a fun airplane. However, if we include the installation weight on the battery, instead of using the cell number, our range drops to 245 kilometers, which isn't too bad. You can see the amount of energy over here in gray. There's lots of 245, so it seems okay. But we had neglected the takeoff and climb energy, which is assumed you were cruising. So if we add that in, we lose a little bit. There's a little energy used for that. So we're down to 202 kilometers. An airplane typically requires a 30-minute reserve Some of these are more. So if we use a 30-minute reserve, we have to have enough energy to cruise for 30 more minutes to an alternate airport. Well, over here, that's about, it looks like about 35% or so of the energy is just sitting in reserve, we can't use it. So our effective range of our little mission drops to 96 kilometers. That's starting to not get you very far. Oh yeah, we forgot that 10% top, 10% bottom we don't want to use, and if we don't, so we take that out, put that in here, we're down to 47 kilometers. We say, oh, well, it's not a brand new battery, it's 10% down, our range is down to 23 kilometers. That's not very much. Then, if we want to say, let's not have let's be a conventional airplane, let's do a vertical takeoff airplane, like an air taxi. We plug those numbers in there, we make a couple of adjustments for weight, a little bit on drag. We have negative range. So we eat into the reserve to even bother to take off. We actually change the reserve to be actually less. But we don't have an airplane that works. Right? So at these kinds of assumptions, I don't have any airplanes that would do anything with. Right? So this doesn't look good. Now, if you have better batteries, like 400 watt-hours per kilogram instead of 221, our conventional airplane is back to having a 200-kilometer range. And even our vertical takeoff airplane can now go 70 kilometers. So that can get you from one side of town to the other. This is actually not too bad. If you can improve the aerodynamics of the airplane to 20 instead of 14, which in itself is pretty hard, we can get up to 350 and 150 kilometers. So there's potential here. But you can see how the assumptions and the available battery-specific energy can make your concept practical or completely infeasible. This is the kind of thing that you need to do if you're running an investment company and they're asking you to invest $50 million in developing a new electric airplane. Somebody needs to be running these kinds of calculations to see if they're telling you the truth about what the airplane is. Okay, and then this is just going back to that same chart showing the trend. Right? So this is what we essentially created. We did a couple of examples. Okay. Infrastructure is also a big deal. We talked about it a little bit in the morning. I mean, airports have electric power, but they have the kind of electric power that you might have in your garage. They don't have the kind of electric power set up that you might need to charge some of these airplanes. When you buy an electric car, you often have to install a special outlet in your house. You may have to put some extra circuit breakers. You may need an extra dedicated line to power your electric car. And only the smallest of airplanes are going to use the kind of power and energy that your car does. Anything that's beyond the smallest airplane is going to use more power. Going to want more power than even the cars. Actually, more like one of the big electric trucks that they're developing. And so airports are going to have to change if they electrify, right? And so that's a big deal. The airports are doing studies to figure out what they need to do to accommodate electric and hydroelectric airplanes. So they're coming up with plans of what they might need to do that. The community is trying to work with the ground transportation people, trying to get some standardization of plugs and different things like that. But if we ever electrify large airplanes, we're going to need our own and even bigger plugs than they use in trucks. So a lot of activity potentially in order to make that happen. A reason for the industry to resist, kind of like the reason, we don't want hydrogen because we need new tanks and a whole new infrastructure. Well, we don't want to put in a bunch of high power electrical stuff either, because that's going to be hard to do. The advantage they do have is, there's already electrical system that, that comes into airports. It may not be big enough and it can be upgraded. So, what else? Mechanics and ground crew are not used to dealing with the voltages and power levels that would be present in electrified aircraft. Talk to some people, and it's kind of like the old airplane mechanics they don't want to hear about this stuff. They spent their whole career, they don't want to deal with 1,000 volts at a time. They just stick with 100 volts, 24 volts. A lot of enthusiasm, though, I think among the younger people, the younger mechanics are interested in being trained in the new technology and stuff. But it shouldn't be, things like training shouldn't be neglected. Bringing along all the people that are needed to make these is also important. As we said this morning, these infrastructure considerations apply to any of the alternatives. All right, we have this matrix, right? So let's fill a little bit of it out here. For electric airplanes, what's the advantage? What's the opportunity? Fully electric airplane, there's no CO2 emissions directly coming from the airplane. Hybrid electric airplanes, depending on the degree of hybridization, we call it, right? How much of the energy is coming from electricity and power, how much is coming from burning fuel. The hybrid just has reduced emissions because you're saving some fuel. Depending on the degree of hybridization, it may not be much better than a conventional airplane. Okay. Biggest challenge for the electrics is battery-specific energy, leading to reduced range or payload. The safety of the batteries, been a lot of problems with battery safety. Component power and specific power, right? Remember, because of all those extra blocks that we added into the diagrams, the heavier those are, the harder it's going to be for the electrics to compete. So the power to weight of all those components, in fact, there are so many, that's important. Thermal management, we stressed, right? All of the waste heat has to be taken care of with heat exchangers, and you have to account for all that and make sure that it's going to work. And infrastructure, right? Electrifying everything is a big deal. And the hybrid has basically the same challenges. It's just, I think it's a little less sensitive to the power to weight and things like that because it doesn't use as much. All that. So those are the opportunities and challenges. And then we covered these earlier, right? Biofuels, synthetic fuels, methane, and hydrogen. So all these have opportunities. Most of them are not proven, right? They're just being investigated. And they all have challenges that are being addressed as they're going. The way to address them, right, is to do them, right? Get away from PowerPoint, to get in the lab first, then to fly small, then to fly medium, then to fly big. That's the way to address these and engage with everyone that has a stake in it. Right? The electric companies, the airports, the regulators in different countries, the policymakers, bring all those people. That's how we can address that. Academia has started to catch up on these things. There are books that are starting to come out. I mentioned this one on the left. There's some sustainable aviation material in there. There's a book on electrified aircraft propulsion that covers in detail some of the things that are in here, and also they're in the short course that I do. I think our short courses get into more detail than you will find in any of the academic textbooks. Academia is starting to catch up. We're doing okay on time. I'm going to play this video. This is going to work. This is a video that Airbus did several years ago. It actually won awards for industrial video production or something. So it's it's cartoonish, and it's actually some good content in it. I'm going to play it and go through it a little bit. It talks about the history of aviation and how it is evolving toward electric and hybrid electric, and talk about some of the way it needs to work with aircraft regulators. I'm going to play this, if it works, and I'll turn it over to questions.
Today, we are going to talk about electric and hybrid electric propulsion.
Hybrid what?
In the future.
Okay, is the echo too bad? Are you guys able to hear? Okay, I'm not sure how to hear it. But... Okay, so I'm gonna play it, and we'll have question and answers.
Electric and hybrid electric propulsion are going to be part of our lives. To understand why and how, let's take a look at the past. For a long time, people have dreamed of flying. To make this dream come true, flying machines were imagined and built. The introduction of engines provided the thrust necessary for these machines to take flight. It was no longer a dream. People could fly. Over the years, the technologies used to produce thrust have changed, including two major revolutions in aircraft propulsion. The jet engine was introduced on aircraft. By ejecting air at high speed, the turbojet allowed planes to go faster, further, and bring people closer together.
Le premier Airbus a donc volé aujourd'hui et a bien volé 3 ans et 5 mois après la date de lancement, ce qui est, je crois, un gros succès.
The introduction of the turbofan in aircraft improved efficiency and reduced noise for better cabin comfort. The fan is coupled to a gas turbine to split thrust between the fan and the high-speed air jet. 80% of the thrust is provided by the fan. Efforts to improve efficiency and reduce noise led to the increase of the mass flow through the fan and to decrease the mass flow through the core of the gas turbine. Increasing the bypass ratio has allowed the improvement of engine efficiency and therefore aircraft operating costs. Coupled with huge advances in aircraft design, these propulsion system improvements have enabled airlines to create business models that significantly lowered ticket prices, thereby democratizing air travel and also substantially decreasing aircraft fuel burn and CO2 emissions. Since the start of the jet age in 1950, this reduction has reached 80% per seat. Now that we know the past, let's see what the future holds. Today, one of our airplanes takes off or lands every 2 seconds. The number of passengers transported by air each year has reached 4 billion. Air traffic will double in the next 15 years. Faced with these new challenges, Airbus is researching technologies which further improve the sustainability of our products and strives to develop next-generation technologies to reduce our carbon footprint by 50% in 2050 compared to 2005. The third propulsion revolution.
Right, that was the old goal of 50% reduction by 2050. Now, they've imposed on everyone 100% reduction, net zero carbon.
Has begun. It's not a dream, it's a reality for the future. Our teams are working on several new propulsion architectures. Among them, serial hybrid electric propulsion consists of a fuel-powered gas turbine, providing power to an electrical generator to produce electricity. This electrical power is then converted to power a motor that drives a propeller or fan to provide the requested thrust. Parallel hybrid electric propulsion is based on turbofan technology. The fan can be driven by the turbo engine, by an electric motor, or by both at the same time. Like the serial hybrid propulsion architecture, the electrical energy drawn by the motor can be provided by a fueled generator. Batteries may also be used in such architecture. The full electrical architecture does not include an electrical generator nor a gas turbine. The energy provided to the motor is stored in a battery. These technological breakthroughs will improve sustainability. Enabling this third revolution in aviation will require new ways of collaborating among airframers, engine manufacturers, and system suppliers. An airplane is only allowed to fly if it meets a set of requirements imposed by authorities. All aircraft are subject to these rules and their associated acceptable means of compliance. However, these methods were developed in the context of traditional architectures. Does the introduction of hybrid electric propulsion make them obsolete? As representatives of the industry, we have an opportunity to work together to establish methods that are suitable to introduce hybrid electric propulsion architectures in our aircraft in compliance with airworthiness regulations. Together, let's make the third revolution a reality.
Okay, interesting. All right. So I thought the little video at the end, it's a little cartoonish. In some ways, it summarizes some of the things that we went over today. I guess I want to conclude with the idea that often it sounds like people say, we have an electric propulsion system, therefore we are sustainable, or we are green, or we are environmentally friendly. And really that, it only applies if we have the development of a sustainable electrical grid, renewable electrical grid to charge our batteries, things like that. And also if we're able to reduce the amount of fuel that we're burning in these hybrids. So something that's a strong hybrid is still going to burn a lot of fuel and isn't going to help nearly as much. So just by claiming that you are electric does not mean you're necessarily green or environmentally friendly. So that's another distinction that has to be brought out. Okay, open it up for questions. Yes, sir.
Yeah, do you think, it occurs to me that there might be some lessons to learn from how long it took electric cars to really enter the mainstream. It seems like overnight, all sorts of electrical vehicles, skateboards, scooters, cars, have come onto the scene, and it seems like it was almost by magic, that all of this stuff cropped up overnight. And of course, the most successful car maker in the world was a total outsider from the legacy automobile industry. And I'm wondering, it has to be a combination of mindset and some sort of technological development that was there at the right place at the right time. And I'm wondering how those two things might play into this question of electrical propulsion for aircraft.
Yeah. Well, I mean, it's all a good question, right? I feel like sometimes I have more questions than answers. But one of the things that we try to learn is what are the questions, right?
Sure.
And what things to watch for. How can you see progress along the way to getting there? I would say also policy, government and international policy will shape these things too, right? And provide incentives to accelerate the business side of things. And so that's an important thing to look at. One of the things that's happening, one of the things that's restricting the use of cars is in infrastructure to be able to charge readily wherever you have your electric car. And they're just starting to do that, but only Tesla has a good network of chargers right now. All the other networks are pretty bad. You can't be sure that you're going to have a charge when you show up at the hotel, right, 300 miles from your house, and you're not sure you're going to be able to charge on the way if you need to. So, yeah, a lot of these things play together in that way.
Was there a technological leap that made so many of these things possible?
Well, one of the things that happens is the cost has to come down to the point where a politician can put a penalty or a tax credit on it to make the business case close.
if an electric vehicle always is going to cost 3 times as much as a gas-powered vehicle, it's not going to happen. But if you can get it down where it's 20% more expensive, and you can get a tax credit for buying a car, then that's going to happen probably. And then you hope that you get the economies of scale to the point where then it becomes competitive without the tax incentive. That's kind of what happened to cars. And I don't know, right now it's hard to get an electric car. It's in high demand. We've also had that problem with gas prices going up and down over time. Price of oil going up and down. When the price of conventional oil and gas is very expensive, a lot of money goes into alternatives. When the price goes way down, it dries up. And so that has affected the uptake of these technologies as well.
And one more question, if I may. At the beginning of your presentation, you were talking about global warming and and sort of the environmental motivations behind electrifying. The carbon credit business, do you see that as, because it looks like we're years away from a practical aircraft being able to become commercial and have commercial applications. That feels like it's quite a distance away from us. As we're racing to reduce CO2 in the atmosphere and that sort of stuff, do you have any awareness of a marketplace that, where there's an interest in carbon credits as a way of bridging where we are today to this hopeful world of tomorrow?
Well, there's a lot of activity in the area of carbon offsets and things like that. I mean, the whole framework has been put in place. It's not worldwide. It's in different segments or different places, areas of the world. The EU has a scheme. My understanding is the price is still too low to really drive a lot of the decisions. But it's probably coming up. That was the plan, was to start it out low and then ramp the price up over time in order to make it have more bite.
You're talking about the carbon credit itself?
Yeah. And California has their own system that they do. That's one reason why companies leave California. But there's incentives put in place in other places. We saw this morning. I think I showed it this morning. Yeah, I showed a chart. It had South Korea's system and all that. So it's going on, and it's clear, right? Those wedge charts show all this improvement that aviation is going to make, and if they don't, they have to fall back. Either begging for forgiveness from the regulators around the world, or they have to start paying more for carbon, buying offsets from someone else.
Europeans tried to do it several years ago before the pandemic, but they backed down. They tried to impose these credits on U.S. airlines coming in there, but nothing happened. They just kind of, budged down and didn't do anything.
That's true. Yeah, the pandemic disrupted things. The war in Ukraine has not helped because it disrupted the supply of energy and changed all this stuff that people stop decommissioning their coal plants because they needed the energy, all these things. So it can be disrupted, right, in different ways.
Hi, I had a question. This is Vinod Mangle. Can you hear me?
Yes.
Yeah, my question was, you talked about emissions during flight, and you try to compare it with conventional, with e-aircraft, etc. And typically, as in EVs, they talk about cradle to grave emissions. What do you have to say about that for electric aircraft or eVTOLs in particular? Any clue? Or you can expand on that? Cradle to grave emissions is what I'm talking, not just the flight emissions.
Yeah, sure. I talk more about that, right, in some of the longer, more detailed courses. What's unique about airplanes, especially if you're talking about commercial airplanes, is they spend so much time flying and burning fuel, for example. They're in the air 10 hours a day or more. That dominates all the other phases of their life. So the energy that went into making the airplane's parts and putting the airplane together ends up being much less than 1% of the total, say CO2 emitted over the entire life cycle of the airplane. So that tends to make a difference in the aviation. He's going to focus more on the operational phase. Cars are not the same. Cars are more like 10% of all their emissions come from their manufacturer. 90% comes from the driving and burning of the fuel, and other things have different ratios like that. So I think that's why, although Boeing will brag about how they've reduced the energy and emissions and water use in their factories, all that stuff, and that's all good, but it doesn't really affect the total impact of aviation very much. Well, you mentioned EV tolls. That is a really, really good question. The EV tolls also need to worry about, and so does all aviation, but EV tolls especially need to worry about comparing to ground transportation alternatives. And then it's unclear, although I'm seeing more and more research kind of every month or two, I see a little bit more on it. Flying an EV toll from the airport to downtown compared to riding in a car or a train, these things are similar in magnitude, the amount of energy per person per mile kinds of things. So it's really not clear how environmentally friendly an electric EV toll is going to be. It certainly would be better than riding by yourself in a rental car. I think that's probably clear. But compared to if you were riding in an electric shuttle van would be way better than flying in an EV toll around the town. But then you have to probably consider the time value of money if you think you could fly faster than you could drive, and so then that enter the calculation, and then it would get complicated. But yeah, it's a good question to ask, right? In your EV toll, how is it going to be environmentally compared to something else? So those are all good questions.
You also, what I'm wondering is when you said parts, the emissions for flight to cradle or cradle to grave is typically to do with lithium ion, the making of lithium ion batteries, right? If it is electric, whether it's aircraft or eVTOLs. Has somebody made a full study that take into account everything? I've seen that in EVs, and they finally have concluded that yes, it has less total emissions life to cradle to grave for EVs. But is that true what you said in 90% or more, 99% for aircraft is cruise or flying, and only 1% of emissions come from other part making business? Is that true of e-aircraft or eVTOLs? If you include, making of the lithium batteries, which
yeah. Well, the thing with the batteries is they have a limited life, and so the airplane may go through, a battery set every year or even more than once a year. And yes, that can start showing up as a bigger driver. It depends on the life of the battery, how many cycles you can get out of the battery. But yeah, that needs to be looked at. It needs to be tracked. And it can start showing up as a significant, the battery replacement, the multiple battery replacements can start showing up as a significant contributor. So yeah, that's a good point to make. I'll reiterate the point that I think I mentioned earlier, is that yeah, the studies clearly show that electrification reduces environmental impact, CO2, climate change, and all that stuff under almost all the realistic sets of assumptions. And there are bad studies out there that show the opposite. There are bad studies that show that wind turbines are terrible and solar panels are terrible and batteries are terrible. And most of those are not correct. You could probably get someone to argue about it, but generally they're not correct. The concerns about batteries that are pretty valid are some of the ones involving the use of metals, that are cobalt and different things that may be mined in an improper, unethical way in some third world countries. That's a good consideration to worry about. And there may be environmental damage as well as child slavery and all these things that go on. I'd say having a more robust supply chain. They're trying to figure out, are we getting the battery materials from the right places that don't do that kind of thing. And the other thing they're doing is redesigning batteries to not use some of those metals and things that are with rare earth metals and things. And so the system is trying to accommodate and be realistic and eliminate some of the issues that they might be having. But you hear those concerns too, right, about batteries. The thing you hear about batteries is the recycling. There's not as much battery recycling right now as there needs to be. The market is about ready to really just explode because all the electric cars are going to start coming offline to be recycled. But I think it's coming together. People are trying to work that. And you know, if you're worried about the cost of lithium and other materials in batteries, well, one source would be the batteries that you're going to be recycling. And so I'm a little disappointed it's not happening faster, but that recycling of batteries is a big deal, and will be a sign of success that we've turned everything into kind of a circular kind of economy once we do that. And airplanes especially are going to have, you know, a lot of batteries and a lot of big batteries.
All right, thank you.
Okay, thanks.
Dr. Bradley, do you see a potential in photovoltaics on wings and fuselages?
Oh yeah. Get that question a lot. Generally, the solar panels are not, they don't generate enough power per area to help out very much. But that doesn't apply to all types of airplanes. During lunch, we mentioned niche applications of airplane missions, like high altitude, long endurance airplanes. I'm involved in sort of tangentially to one. The mission is to go to high altitude, like 50,000 feet, and gather all kinds of samples from the air to gather data for validation of atmospheric chemistry models. And so you spend a lot of time, very high altitude, you can have big wingspans, low power requirements, and you can fly around. And for applications like that, all the time, solar is looked at, and it looks pretty interesting. Otherwise, generally, it's better, you know, the ideas of taking the grass at an airport and turning it into a bunch of solar panels, using that to charge airplanes probably makes more sense than putting the panels on the airplane. But it's one of those things that I think periodically you should relook at how the technologies have improved. And at some point, does it make sense to put a small solar panel on part of an airplane to do something, say, when it's being, to cool it down when it's sitting on a runway in Saudi Arabia in the summer, it's getting really hot? Can you use that solar panel to drive a cooling system just passively sitting there? I think that's the kind of thing that should be periodically kind of reinvestigated. So there may be some potential, but powering a transport airplane, solar panels, no. But some of the special mission airplanes, yes.
Thank you.
Yeah. And there's people looking at that pretty actively.
I think there's a question online. Shogun, would you like to speak out? He said he will ask the question again. Also, there is a question in the Q&A. You just brought it. About chart 13.
Is this the chart? I'm not sure I'm seeing. Chart 13, if it's this one, that's the total propulsion power of the airplane. If the airplane was fully electrified, it would need those kinds of numbers. What I didn't talk about was, I mean, aircraft already have electrical systems. They have hydraulic systems, they have pneumatic air systems, they have all these different things going on the airplane to to drive the different, we call them subsystems on the airplane, the cooling, air conditioners, I don't know, the avionics that control the computers, the flight control, actuators, all those things are driven by either hydraulic power or electrical power. So there's a whole bunch of systems on board anyway. So we're not really talking about, that typically would be a small fraction, a small percentage of the powers that we're talking about to drive the entire airplane. So that might be 1 to 5% of the power of the airplane might be going to those other systems. So I don't know if that's kind of what the question is about, but there's a whole other area I didn't talk about. It's electrifying those subsystems is one of the things. 787 did a bunch of electrification of systems for efficiencies, and that trend continues, but that's a different development path than what we're talking about here, which is taking primary propulsion and making it electric. But there's a lot of relationship between the two.
Mr. Min Chan has another question. Mr. Chan, go ahead.
Thank you.
Okay, thanks.
Min, go ahead.
Yeah, okay, sure. I was thinking that you could just read my question, but that's okay. So where do you see carbon nanotubes coming in for energy storage as batteries?
I don't think I know. In terms of, I would say that's the technology that's inside the box that I don't know enough to comment about.
So we start pushing that. That might be a good technology to push, don't you think?
Well, do you have some experience in that?
No, I don't. I'm just asking,
Yeah.
I know that there's a lot of research in that, and maybe, we know that, solar energy is really, solar panels on an airplane is not really an answer. And neither is batteries in itself because they're heavy as heck, but, carbon nanotubes might be an answer. And might be us pushing that. Maybe the aerospace industry pushing for that. I don't know. Right now, aerospace industry is not pushing for any of that stuff.
Well, what attribute of carbon nanotubes are you talking about exploiting? Are you talking about conductivity? Or are you talking about strength?
Well, I'm not talking about strength. I'm talking about, energy storage capability, lightweightness, having the surface area to be able to having a huge surface area.
Oh.
So that's what I'm talking about.
Yeah, I don't think I know. I think there's plenty of people, though, incentivized to improve energy storage, though, that should be looking at that.
Yeah, that's what I'm thinking of.
Yeah, I don't know. I mean, that's one thing I sort of teach my students sometimes is every time you dig into an airplane and you look at one aspect of it, you find that there's a whole bunch of complex system optimization work that's been done. And it's not even in the field that you understand that other people have done. It's an area of specialization. So one example I had is the electric motor, which the airplane person models that as like this black box that has 3 different parameters sort of define the electric motor. When other people spend their entire career designing and optimizing the electric motor, it turns out the electric motor involves the optimization of the design of mechanical engineering and structure. Everything's spinning very fast. It has aerodynamic effects inside that you don't maybe expect, plus all the electrical things going on. So pretty much you find out whenever you dig into any of these areas, structural design, looking at material development, those are all very interesting areas and very.
Yeah, I agree with you. I remember in the early 80s, not only Lockheed Martin, or at that time Lockheed, but I know that Boeing was also studying all-electric aircraft. And that was early 80s. And we still don't have an electric aircraft at this point in time.
Yeah, but those nanotubes are just gonna look superficially, it says it has potential up to 10 times. Increased lithium storage capacity.
Oh, is that right? Okay.
Yeah, so let's say you have a 300, 400 kilowatts, you increase 10 times, it's 3 megawatts, which gets you to the lower threshold for, I don't know, short range, I don't know, applications maybe, but still it's well below where it needs to be for long range aircraft, like for example.
Yeah,
well, none of this is for long range.
No, yeah, true, yeah.
Yeah, I mean, okay, your point's good, and there I don't understand, I can't say about the nanotubes. What I can make a comment that constant stream of people coming to like Boeing, for example, pitching their technology for improving batteries, for a new breakthrough battery technology, and you see those kinds of things every week in news releases, university studies, and all those things. And so there's a lot of activity, but you have to be pretty skeptical about what's really going to come. So yeah, I don't know.
You could spend another day with battery experts on nanotubes, and they're also a hot topic for fuel cells.
Oh, really? Okay. Well, see, I'm learning, right, from my own class, so that's good.
No, absolutely. I mean, fuel cells, carbon nanotubes, all that stuff is out there. And I'm just wondering, we talk about electric aircraft, and as I said, I started working in the early 80s, mid 70s, early 80s, and electric aircraft has been studied from almost 50 years, and we still don't have one. And that's because of the energy density and energy storage problem, really, more than anything else.
Well, I mean, we have a few, but they're very limited. You can be trained as a pilot in a trainer airplane for some of the early phases of your flight. They have fully electric airplane, fully electric training aircraft, not certified everywhere in the world, but in some places. And they're experimental aircraft that you can fly in, and there's a bunch of demonstrators, that are flying or getting ready to fly. So there's a lot going on, but we definitely don't have something. What would you call it? A commuter airplane or a good general aviation airplane that's suitable for mass production. That's true.
Okay, there was a question earlier, but this gentleman has left. Mr. Paul Pereira from UK. He was with a company called Aero. He was asking if you could share a few words about superconducting.
Oh. Again, right, I'm no superconducting technology expert. The advantages of superconducting are you can essentially take those losses that we had 95% efficiencies, and you can take them all the way up to 99% or more, because you reduce the electrical resistance in the component. So it's really interesting to be able to do that. So that's good. What we often find though is that you have to, it's the cooling, right? You have to have a way of getting and keeping all the parts and everything very cold so it can be superconducting. That's why the synergies with hydrogen are interesting, because hydrogen starts out very, very cold and it's suitable for superconducting temperatures. If you don't do that, you have to actually, if you're not using something, a cryogenic fuel like hydrogen, to get to superconducting temperatures, you have to build a cooler to cool things down to that level. And that cooler uses energy and it works against your efficiency improvement that you would get from doing it. So that becomes a big study in looking at it. So that's one thing that you need to think about with the superconducting, right? Make sure you include all the pieces to make the superconducting work. The synergies with hydrogen are really interesting, so that's good. The other thing that we're running into, I think, is sometimes as the power goes up and you try to scale the electric motor up in size, for example, you can't get the heat out of it. The geometry is it's confining, and you can't figure out a cooling scheme that's light that can get all the waste heat out of it fast enough. But if it was superconducting, it would only create a fraction as much waste heat, and you wouldn't have to worry about that. So it's a different design approach that might be used for the larger, higher power electric motors and generators and things like that. So that's where superconducting plays nicely in potentially future activities.
Yeah, I do have a question. Earlier you mentioned boom supersonic, or you trying to say that the reason they could not get a company to make an engine for them was because of this issue, or it's actually different?
No, I don't think I said that. I said they were out of business.
Yeah, you're right.
And I said that the supersonic companies were using sustainable aviation fuel as a way to mitigate the environmental negativity about flying supersonic. Yeah. I think the problem that supersonic guys have with the engine availability is the market is very small. And so GE or Rolls-Royce or somebody, they don't want to spend a lot of money on the new engine development for a limited application. What else would I say? I was talking to Airbus just, I don't know, earlier this year about an unrelated topic. But one of the things we were doing was saying we could calculate the environmental impact of a supersonic airplane as part of the study we might do for Airbus. And Airbus was like, no, we don't want anything to do with a supersonic airplane because it's terrible for the environment. So we don't even want to talk about it. And so I'm very skeptical about how successful supersonic airplanes are going to be going forward.
Yeah, because they were kind of big, like 2 or 3 years ago.
Well, yes, several companies were making significant progress involved. They had Boeing as a team. One of them had Boeing as a teammate. One, different. Lockheed was working on it with another one. These things are going on, and I think it's sort of. I think they're losing steam on some of those things.
Yeah, you're right. Sorry, I just try to, verify a little bit.
Yeah, no, it's, yeah. Even worse would be hypersonic commercial airplanes, even worse for the environment. There's some people that have mentioned that as well. Yeah. Okay.
Oh, let me see one more.
Yeah, I mean, if anybody, like, we're at the time, aren't we? If anybody needs to go, they're welcome to leave if you guys need to go. But I'll stick around for a little bit longer if there's any more questions.
They just, online just saying thank you so much. Yeah, there are many people saying so.
Okay. Thanks for hanging in there and listening to me. So thanks.
Okay, thank you so much. This is really wonderful presentation. So let's thank Andy to show our appreciation. Yeah, our section, Los Angeles, Las Vegas section of AIAA, really thank Dr. Bradley for this wonderful presentation.
Am I getting wiped out by this? By the projector, or does it look okay?
Yeah. You might want to, step over.
Yeah.
It was blinding me, but I didn't know if it was affecting the picture.
Sorry, it was like putting like a patch over your eye. Why don't you go more this way?
Go ahead.
Oh, maybe in front of the
Yeah.
Yeah. Go ahead, Ken. Get it.
Oh, I don't have to be there.
Yeah, you do.
Okay.
Thank you.
Thank you.
Dr. Bradley.
All right, no, thanks.
It's a wonderful presentation. Thanks, sir. Truly appreciate it.
There you go, Ken.
Maybe not anything we can do for you.
Okay, very good.
Thank you.
Thank you, and for all your work too.
Great.
I mean, everyone knows how much work Ken does. There's nobody that works harder than he does.
For everybody, for you. for the community, for
Thank you.
aerospace.
Yeah.
Alright.
Right. So if you are interested in joining AIAA, you have not a member yet, please okay, talk to me or sign put your name, your address on the back in the sign up sheet. Thank you.
Oh, thank you. Professor, will these slides be available?
You send me an email,
Okay.
I will send it to you. I don't know, Ken, are you posting a recording somewhere?
We'll post a recording.
Okay.
So I think that's as good as the